So good morning. Good morning, everybody. Thank you for coming. Please bear with us until we start. We start in about 15 minutes with the keynote address by Prof. Alan Macdonald. And so the first 15 minutes, I will use it as a buffer to allow in people to come. And then, please bear with us. And yesterday, for those of you who didn't participate or attend yesterday, it was an exciting day with an opening address by Dr. Kalist Tindimugaya on behalf of AMCOW and the task team currently drafting the African Groundwater Program for the post-2025 Africa Water Vision. And he has highlighted the 4 pillars of the program, one of which is related to this Congress, or this conference, is on human capacity building, tertiary level education, and multi-level capacity development activities, the gaps, and what is needed, and how to overcome these challenges. And then that was followed by an excellent keynote address by Prof. Daniel Olago from University of Nairobi, who has highlighted the framework of African hydrogeology, geologic framework for African hydrogeology, and then climate framework, coupling modern and past climates, and how these have interacted in the past to govern the state of water security in Africa, and then under climate change induced by human activities, and what is expected, what is anticipated to happen in the future, and then what does that mean for water security in Africa. And then also tapping into his rich experience in Africa, he has highlighted some key lessons, and what he has, several things, very rich presentation, and he has, making reference to Prof. Alan Macdonald's work on water security in Africa, highlighted, what we have to put in our back of our brains on regards groundwater storage and recharge. And principally in Africa, we have high recharge, relatively lower storage aquifers. So what does that mean for water security, depletion, etc.? And then high storage, low recharge environments. And then in some instances, a combination of both. So that was the message, one of the messages. And then also he highlighted the importance of scale and for the kind of knowledge and information or data required to make decisions on, from community level at a larger spatial scale. And then that fine scale understanding, which comes through the hydrogeology research and data. He has highlighted that clearly. And then, it was very rich presentation. You'll find it. We recommend that you watch it once this is mounted on a YouTube video. And yesterday that has been followed by several interesting presentations, ranging from African researchers doing hydrogeology research at international scale, global scale, to also using geophysics for borehole siting scale and contamination studies, use of isotopes. It was really amazing, an amazing day yesterday. And what struck me yesterday was, while someone was presenting a case in Algeria, the other person who asked the question was from Zululand, from South Africa. these are, if you measure the distance, this is the farthest distance in Africa, from, let's say, the corner in Morocco, Algeria, to southeastern part of South Africa. And then this was really impressive. Yeah? So having this connection, the functions that this conference has in connecting Africa researchers was enormous. And I think this would mean that we'll need to continue this interaction in the future. And this phase was just a learning phase, first Congress, and we didn't know how it is going to turn out. And then what came out yesterday was very promising. And so this is the first of its kind, organized under the IAH. Yeah, yes, Alan, thanks so much for joining, and then for your willingness to provide this keynote speech, Prof. Alan. So I think everybody here knows who Alan is, and is someone who doesn't need to be introduced. Just in case, if there is one person, so Prof. Alan Macdonald is from British Geological Survey, and he is also currently chair of the Burden Commission of the IAH, and is one of the most recognized names in groundwater science. And then his pioneering work has shaped how Africa and South Asia understood and value and manage groundwater. If I put it in the way I see Alan is, he knows how to make the case, and everybody understands hydrogeology. So any conversations that you'd have with him allows you to understand, is it like that? Yeah. Oh, okay. So every word that comes from Alan has, So he has authored many research papers on Africa, on groundwater resilience, water security, and globally cited research from this region, and also from other parts of the world, but also from Asia, and which has both policy and practice significance. So Alan is a figure who needs little introduction, and he continues to influence science and development and policy making on groundwater in Africa at highest level and globally. And he's currently the director for international programs in BGS. And Alan, so so it's your time now.
Oh, thank you, Seifu. What an introduction. I hope I can live up to that a little bit. It really is a great pleasure to be able to speak here, and thanks so much for inviting me to the committee. And I just think it's such a wonderful initiative to have this online Congress. So real congratulations to you, Seifu, and to the whole committee for bringing this together. It's been a great program. Okay, let's see. Entire screen. Are we getting there? Okay, sorry everybody for the delay. As I get right, hopefully you can all see my screen now.
Yes, so, perfectly. Great. Thank you.
Thank you, Olivia, and thanks everybody. So I've been asked to talk to you today about the hydrogeology of basement rocks. And this is some work I've been doing with many other people whose names will crop up through the presentation. So I'm going to speak for about half an hour, and looks like there'll be good time for questions and discussion afterwards. I'm sure there's many people on the call here that know a lot about the hydrogeology basement, who will have lots of good views and points as well. So first of all, the hydrogeology of Africa, and Dan Alago shared a similar slide to this yesterday, but it is good to just remind ourselves of the different hydrogeological units that are present throughout the continent. And you'll see, I've split them in here into kind of four main groups, And you can see that basement rocks occupy about 34% of the landmass of the whole of Africa, much more if it's just sub-Saharan Africa, but 34% of Africa. And actually, in terms of population, though, it is the most important, because actually the basement rocks are in areas where most of the population are. So you have, I think, maybe about 500 million rural dwellers on basement rocks. So it really is probably the most important, certainly the most widespread aquifer across Africa. And although it is present in many other parts of the world, notably peninsular India, where it's used a lot, it really is within Africa where the kind of science of the hydrogeology of basement rocks has really been to the fore. So it really is Africa that's leading the way with the science of basement rocks. So what do we know about the basement aquifer? Well, for many years, and I think for many years, we have known really how the aquifer works and how to develop it. So here's this block diagram that shows a crystalline rock, the bedrock there with no permeability or porosity within it. And it works as an aquifer where it's been weathered and fractured. So either with weathering, with fractures beneath the weathering, or in lineament fractures or fault zones as well. So that's kind of know how the aquifer works. And there's a host of different papers there that have been written over the years. That's probably only a fraction of them, but a number of the papers that have been written over the years describing that kind of behavior of the basement aquifer. And this diagram on the right that I put up there kind of neatly explains how the aquifer tends to work. It looks a bit complicated, but it really is a nice, neat way of describing it. So you've got the profile on the left-hand side, which shows the soil, maybe the fertilitic soils at the top, then the upper saprolite, where the rock is quite well weathered, and maybe into clays. Then we've got the lower saprolite, where it's less weathered, and the sap rock, where it's mostly just fractured, and then down into the kind of fresh, unweathered rock beneath it. And the permeability, the next sort of graph over, shows how the permeability ranges for these different soils. So it's maybe can be quite high in that kind of laterite or ferrocrete, then it can be quite low through the kind of clays of the upper saprolite, and then increases at kind of what we call the base of the weathered zone in that lower saprolite and sap rock, and then decreases in the fresh rock, but occasionally you might get very high yields from maybe some deeper fractures that are present. So this is a kind of generalized framework for the weathered basement aquifer, which I'm sure everybody on this call is probably quite well aware and used to developing groundwater within the basement rocks. And this has served us very well over the last maybe 30, 40 years or so. And we've got techniques to develop the groundwater, to find these kind of deeper weathered zones, which give the higher yielding boreholes. So on the left there is just a classic resistivity kit. So we can use resistivity or two-dimensional resistivity ERT. We could also use electromagnetic methods, which are a bit more rapid, give a kind of rough idea of the thickness of weathering. So these techniques have been kind of well honed and well developed over the years, mainly to develop hand pumps. I actually had to get a picture from the web of a hand pump because I realized that all my many pictures of hand pumps have generally got children or people in them, which we're not really allowed to show now. So that's why I've got a picture from the web of a hand pump there. So we kind of know what's going on with basement, and it's been very successful in providing rural water supply to many people. But then a question kind of arises. Can we get more out? So for the Sustainable Development Goals, particularly Goal 6, which talks about reticulated water to every household, and also an increased emphasis on food security and climate resilient agriculture, can you need more water than just to supply hand pumps? And this is already happening in many places where hand pumps are being replaced by other pumps, higher yielding pumps. So this gives rise to a number of questions then about basement aquifers. First of all, can basement aquifers support this? Can you actually get a lot more water out of basement aquifers? And can we actually predict that? How can we better predict where you could get these higher borehole yields? And lastly, can we then use that knowledge to systematically map hydrogeologically basement aquifers a lot better? So that's really going to be the subject of the talk that I'm giving today, and it's based on work we've been kind of doing here at BGS with partners over the last kind of 7 years or so. And I'm going to split it into kind of 3 different experiments, I suppose, that we've been looking at. But first of all, the question, what yields are possible in African basement rocks? So many of you will know of the well field, or maybe even worked on it in the Dodoma, the Makadaporo well field, drilled into basement rocks, supplying 50,000 meter cubes per day from that well field. And many people have been working on that over the years to both develop that well field and to look at its sustainability. I mean, that's a high yielding well field for any type of rock, but for a basement rock, it's almost unthinkable. But then you just go along the road a little bit to Singida in central Tanzania, and there's many hand pumps there that are actually struggling to be able to supply a kind of low yield of even sort of 5 cubic meters per day. So we have this possible huge range. What is normal? What is a complete anomaly? What could we expect? What other high yielding sources might actually be out there? So our first experiment then was focused on Ghana, and it was to try and understand what yields could boreholes with hand pumps in them actually sustain. What could basement actually yield in this place in Ghana using existing data? So we chose this site in northern Ghana because there was a really great source of data there that had been working there, that had been well-funded projects in northern Ghana for many years, collecting lots of data on boreholes and wells drilled into basement rocks. So there's a really good set of borehole yields, and also lots of really good data on what the boreholes were like, their depth, their completion, the thickness of weathering, and such like. So slide on the picture on the right shows the kind of yields that we're able to get from this basement rock in northern Ghana. And because these boreholes were all drilled for hand pumps, it's no surprise that most of them could sustain 0.1 litre per second, which is not quite enough for a hand pump. It's just about there. But most of these boreholes in this basement rock, could supply a hand pump, and that's that kind of first line there. These are sort of probability density functions. These graphs here, they basically go from 0 up to kind of 100% at the top. So the median would be the 0.5 in here. That's the kind of median of all the data sets. You think of the data set, it's kind of like it's another way of showing a histogram. So you've got 50% there, 20% here, 80% here. So this means that 80% of the boreholes had a yield of just about 60, of under 60. That's the way to do that graph there. So 30% here of the boreholes could sustain actually more than 1 litre a second, which is quite a high number actually. So 30% could sustain greater than 1 litre a second, and a very small proportion, about 1% of this area, could sustain a yield of 5 litres a second. Now, I hadn't actually looked into recharge here, so it might be that in other studies looking at recharge, it might be that these water levels would deplete. This is the kind of instantaneous yield you would get if you started pumping it. So this was really quite interesting to give this kind of systematic view of basement yields in this area. So we could see that of these hand pump equipped boreholes, 30% could actually sustain a much higher yield of 1 litre a second, and maybe could be useful for a little bit of small scale irrigation or reticulation. And a very small number might have been more useful for a town supply or such like. And this was all published in Water Resources Research by Marco Bianchi. So the next thing we did with that piece of work was then to try and work out what was it about the basement aquifer that gave the higher yields versus the lower yields. What was it about it that actually determined whether you got a higher yield or a lower yield? So we built a mud flow model for each individual borehole, and then we parameterized everything using statistics, so stochastically, and used sort of Monte Carlo simulations to work out exactly what kind of profiles were giving these kind of high yields. And just to cut to the very end here, the key factors for a normal borehole, so a borehole, I think less than about half a litre per second, it was all about the regular thickness and that permeability at the base of the weathered zone. So how fractured it was at the base of the weathered zone really determined the possibility for the yield of the boreholes. But actually, for the much higher yields, where you got greater than 1 litre a second, other things were important. It was the water table depth was really important. How deep was the water table? So how much of that weathered zone was actually dewatered? That was really important. And also the aquifer extent. How far out could the cone of depression go before it hit either a non-weathered bit or another cone of depression from another borehole? And lastly, of course, recharge. That was really important as well for much higher yielding boreholes. So this was quite a sort of nice way to end this experiment, to see, well, these are the factors that are important. Not a great surprise on the permeability of the sap rock and the regular thickness, but really good to have that confirmed. And then these other factors for the much higher boreholes. So we came out of that work realizing that basement can support higher yields in places, which we already kind of know, I suppose, from Makataporo and other well fields that there are. But we also know what some of the significant predictors are. So, question now, can we actually map these differences? So crystalline basement rocks come in all shapes and sizes, and here's just a few pictures of some of my favourites. If I'm giving a lecture to students, I'd be asking them to identify each one of them, but I'm sure each one of you can identify them at home at the moment. So we've got our gneiss, we've got an oggen gneiss, we've got mica schists, we've got these sort of big kind of banded gneisses in the bottom picture there, but also have things like phyllites and higher grade metamorphosed rocks. And then of course we've got the soils over the top, the sort of ferrocretes or sort of more ferrosilicic soils, more sort of black smectitic clays, Wimbuga clays, and then of course some kaolinite clays as well. So we come in all sorts of shapes and sizes, the basement rocks. So that makes us think, well, can we actually map out these, and does it actually affect the hydrogeology, or is it not really related to the lithology? How related to the lithology is it? And we draw on some lessons from peninsular India, where there's been work there for many years, and we were working there for a while with Shekhar and with Veena in Bangalore, looking at some of the basement rocks there. And on the left here showed that in this type of rock, which was more a sort of schist, we managed to get quite higher yields than they got in the granite. And with lots of data for this area that done pumping tests at high levels and low levels, so we're able to look at the permeability of the depths. So that gave us some idea that actually these different geology types, we might be able to systematically map differences between them. And we did that for the whole of the Coventry Basin, where we split it up into different geology types, and we got data on the permeability with depth. And then we put that into a model which worked quite well. So that gave us a little bit of confidence that maybe we could actually split up according to different typologies and get some useful information from that. So we went on to our second experiment then to see, can we find these differences, these systematic differences between different areas, and predict them? So we expanded the work from northern Ghana to across the whole of West Africa, when we looked for areas where there was information on the sort of depth of the weathering of the saprolite, where there was information on yields as well in the boreholes. So when the boreholes were drilled, did they do a yield test? Very few pumping tests with transmissivity, so it's mostly kind of yield tests that we relied on. So we looked at that across these different kind of typologies, different kind of areas and different projects, and we split it up into these different geological domains and to look at different systematic differences. And actually, we did find significant regional differences. So by using this approach and the different geologies, we found that we could actually begin to forecast where boreholes might have a higher chance of a higher yield or a lower chance. So this diagram at the bottom here shows a probability of getting a borehole at a different yield. So if you look at D1 here, which is the pink area down here, Liberia, you can see that there's a 25% probability that a borehole will be between 0.1 and 0.5 litre a second. But you have this big yellow bit here where there's quite a high number of boreholes that could sustain between 0.5 and 1 litre a second, and then maybe about 20% that could do 1 to 5 litres a second. But we didn't find anything above 5 litres a second in that area. But you'll see some other areas like D7 down here. You can see that that was more skewed towards kind of higher yielding across 1 litre, above 1 litre a second, and maybe even more than 10% that could have more than 5 litres a second. So that was that was in this kind of more mobile belt in sort of Benin and southern Nigeria, where we've got more mobile bents, organic bents, and schists. So we were quite pleased with that. I thought, well, actually, we did manage to find these kind of systematic differences between them. And that was published in a paper in Hydrological journal that you can read. There's a link beneath there. And we used that information then to work with lots of others to produce this sort of new ECOWAS hydrogeological map for West Africa. So there's many partners involved in this, and we helped put this all together. And we used that kind of knowledge on the basement rocks to split up and divide the sort of permeability of the basement rocks within this map. So this map's freely available. You can probably find it somewhere online. I think it's on the BGS website and it'll be on the BGR website, who hosts a lot of things for IAH. So we used that then to provide information for this sort of map. So that was experiment number 2. So the third thing, and the one we're currently working on, nearly finished, is then saying, all right, you've been able to do this for Ghana, you've been able to upscale to West Africa. Can you actually do this for basement rocks across Africa? And I know many people have thought about this over the years, about different weathering, different surfaces, historical surfaces in Southern Africa and such like, trying to look at kind of different basement rocks. But we thought with kind of the kind of modern data availability in terms of DEMs and such like, and sort of faster computers, could we actually generate these typologies for Africa? So here we collaborated very strongly with geologists. So this is one of my colleagues, Romesh, and several other geologists. And I think it was Dan Alago that said yesterday how important it is for us as hydrogeologists to get back into the field and get back in with understanding the geology. And I would thoroughly agree with him on that. Just trying to understand how the rocks work and the hydrogeology works in the field. So what we did, and what our geologists did, was look at the different factors that will systematically increase the potential for thick weathering. So what are the factors that really increase the weathering thickness? And also, what will impact the kind of fracturing, the likelihood of fracturing within a rock? So is a rock likely to fracture more when it's weathered or less when it's weathered? And is there already sort of more kind of stress within that part of the geology? So we looked at these provinces and domains. So the top one there in terms of provinces, that's looking at the regolith thickness. So to get lots of thick regolith, then generally you'd want a slope that's been stable for a long time. So it's got gentle slopes, low angle slopes. The weathering's been able to occur over a long period of time, and it hasn't all been eroded away. once and you've also had quite a lot of rainfall to allow that process, that weathering to occur. Then if the slopes get a bit steeper into these high angle slopes, then the weathering thicknesses will decrease. And if you get a lot drier, particularly over a long period of time, then there's unlikely to be as thick weathering developed because you haven't had the sort of water into the system to weather it and to remove the products, the clay products. And then if it got into a very recently uplifted area, such as the East African Rift, is a kind of like a special case. Might not have much thick weathering at all because it's been quickly uplifted and eroded away, but it actually it might be quite well fractured because of the tectonic history. And on the domains, that was looking at, well, what's the probability of faults and fractures and shears? And here our geologists say, well, granites tend not to, big massive granites, you tend not to have a lot of just innate fractures within them. Gneiss, you might get a little bit more. Then in volcano-sedimentary rocks, you can get quite a lot more fractures. You've got sedimentary sequences that have been heated up, so there are quite a few fractures in them. And then orogenic belts, so there's been a lot of mobile belts, a lot of movement, then you're probably going to have more fractures. So this was their hypothesis, and they put these provinces and domains together to produce this map for at this scale for the whole of the continent. And we then set off to see if we could test these hypotheses for different areas. So what we did was we went out and we looked for as many case studies as we could. So for our case studies, we needed good information on the boreholes and the depth of weathering that was in each one of them. We needed information on our big data sets of yield as well for boreholes to validate with. So this took a long time, and thanks to many people that kind of contributed data sets to this, we ended up getting good data case studies for about 4 provinces and 5 domains. And this is this kind of probability density function for these different domains. So the main thing to look at this graph, the domains, the yields, is there is quite a big difference, almost an order of magnitude between some of them. So there are differences between the yields of different domains and different provinces in across the continent. So that was quite important. And actually, when you looked into it in detail, the ones that we did forecast to have thicker regolith did often have higher yields in the lower half of the distribution. They tended to have higher yields. That thicker regolith did, when that was predicted, tended to have higher yields. And the ones that were forecast to have more fractures tended to have higher yields in the kind of top half of the probability density function. So in other words, those with more fractures generally had a higher possibility of much higher yields. It didn't make so much difference down the bottom, but up the top, it tended to be a greater possibility of having these much higher fractures, these higher yields within them. So that's where we got to over these looking at these domains. It was an awful lot more work than I think any of us anticipated, trying to get all these data sets together, and then we'd had to develop models for each of these provinces to kind of give that kind of systematic look. But it does show promise, and it has shown that this kind of approach, this provinces and domains approach, does seem to have quite a bit of promise in being able to map out where higher yields are more likely than not. So here's just a sneak preview of the kind of final map we're putting together. So you'll see our colours have changed a little bit in the middle there. These are the kind of data sets that we've got for the different regions. I haven't put the arrows into where they're pointing to, but they're roughly next to bits. Right, these are the ones in Southern Africa, and these are the ones in West Africa and East Africa. And yeah, many people put this together. David Macdonald was a colleague of mine at BGS. He's just recently retired, led a lot of this work, but lots of help from Richard Owen and Seifu, Michael Moore, and the other sort of team at BGS in putting this all together. So that's where we've got to with this kind of third experiment, and hopefully we'll get that paper out sometime soon, and that map for others to look at and to hopefully criticise and improve and refine. So I was going to probably stop there. My time's just about up, but Seifu, you did say if Grant's not around, maybe I can take 5 minutes just to talk about how we could maybe use some of these approaches on kind of more local levels.
Yes, please. Yeah, go ahead. Yeah.
So here's just throwing out some examples of maybe how that kind of approach can be used at a kind of lower scale, either district, site specific, or across a kind of a country or a state. So can use similar approach to this kind of continental mapping approach. So looking at what is the things that control thickness weathering? Could it be the low angle slopes, high angle slopes? Could it be something to do with the climate? Could it be due to have we got presence of rifting or not? And you can look at that at a much smaller scale. You can zoom in to look at that, and our teams and others have done that in different places. But also with the geology, and I think that does show quite a bit of promise, is trying to look at the geology and the type of fractures you get at the base of the weather zone in granites versus gneiss versus mobile organic belts or sedimentary rocks. That kind of fracturing that you get due to weathering is quite important. So mapping it like that seems to be quite good. But also what I'd said in kind of the first part of my talk there about the other things we saw for the modelling was quite important for permeability. Sorry, for yield, which is the depth to the water table, and also where you fit in a smaller catchment. Are you right down near a dambo if you're in southern Africa, or in an Inselberg or something? Where in that kind of localized position do you actually sit? So what we've done a little bit of, our geologists, is using kind of some remote sensing and AI to try and help unpick that. So, for example, this picture on the left by Williams looks at the exposed bedrock. So, in other words, where there might be an Inselberg or where we definitely know there isn't any weathering. So we can use kind of some mapping techniques and some AI techniques, show a bit of promise for that to map at that scale. And also fracture mapping, you can do this kind of work, and Romesh, who was that chap I showed you a picture of before, has done quite a bit of work mapping fractures, both at a field scale, but also then at a satellite scale, and seeing can you actually increase the confidence in kind of mapping fractures as well. And I think that shows quite a lot of promise. However, I'd like to pose this question really, because we all get very excited about satellites because it's space, and we all love space. And Grace has been really helpful, kind of looking at sort of large scale variations in water availability. But what is the most important thing for hydrogeology? And I thought I'd get a nice picture of Seifu in here as well. So, is it satellites, or is it doing the groundwork and getting transmissivity measurements and recording field boreholes, that sort of bread and butter of hydrogeology? And if I have to choose, and luckily we don't have to choose, we kind of have both, but if I had to choose, I would always go with the borehole information, is doing pumping tests, recording thickness of weathering, when a borehole has been putting in. This is the gold dust for hydrogeology. And I think we'll only be able to understand our basement rocks and the hydrogeology of basement rocks better and better if we get this sort of information. We're not going to be able to do it all from satellites. What really is required is that information from individual boreholes, doing the pumping tests. And there's a great example here from Micah War's work in Uganda, where he went back with Joseph, his research assistant, and they analysed pumping, I think about 800 or 1,000 pumping tests from completion tests across Uganda. And these, I think they just chose about 12 districts here. And this gave such rich and useful information, getting that transmissivity data to show us again the variation of transmissivity and the differences between different districts and different geologies. And this really then can help implement, whether you're putting solar pumps in, whether that's going to be sustainable or not. So doing this kind of work and getting the pumping test data together is so crucial. And from his work, you could show it. So transmissivity 1, just about can do a hand pump. So you can see for these pumping tests that actually for some areas that even struggle a lot with a hand pump. And that is maybe a small scale irrigation work, and there's only a few. And then the very high yields, there's not that many that could do a much higher yield for a town supply or such like. So in summary, well, first of all, thanks everybody for bearing with me to the end. And we do know broadly how to develop crystalline basement for hand pumps. There's been a great kind of generalized model for how it works, and we've got geophysical techniques that kind of help us work out where the thickness of the weathering is thickness and where a borehole could be sited for a hand pump. So we kind of know roughly how to do that. We know it needs to be weathered, needs to be fractured. And we also know that you can get much higher yields sometimes where you get very large fracture zones like the Macdonald well field in Tanzania. But there are new challenges, mean that we are wanting to site boreholes with yields greater than half a litre a second. And we want to know, can some of these hand pump equipped boreholes be transformed into higher yielding boreholes? So I'd say from the work that we and others are doing is that we can actually map the hydrogeology basement better using typologies. It is possible. And from the kind of work that we've been doing and others, I think maybe approximately a third of boreholes with hand pumps could actually produce greater than half a litre a second. But there is great variability between the different typologies. Some typologies might be much higher than that. And for some, you might even be able to get 5 litres a second or more for maybe 10% of the kind of site. So for some typologies, much higher potential for getting good boreholes that might provide sort of reticulated systems. And finally, just analysis of routine pumping test data is just the best thing. It's fundamental for our understanding of the hydrogeology basement and for any kind of future maps or understanding that's done. Okay, well, thank you very much, and thanks for allowing me a few more minutes to go over time. Thanks.
Thank you so much, Prof. Alan, for this enriching presentation. And I'm sure there will be several questions. And let me start with my own, Alan, about linking this back to the SDGs and possibilities of using sustainably for other minor productions. So, yeah, how do you see that?
Yeah. Well, I think I start from the viewpoint that it's already happening, in that there's a lot of pressure from donors and others to put in higher yielding boreholes and to transform hand pump equipped boreholes into higher yielding boreholes. And that worries me, and I'm sure it worries a lot of us on this webinar, is that can often be done without working out, is it possible or not? So there's lots of examples of quite high yielding solar pumps going into crystalline basement boreholes, and then them not producing what they should, in fact failing and causing lots of problems. We used to call them white elephants, didn't we? These kind of schemes that are relying on quite high yields from basement rocks because they've got the technology, the solar pump, be it a solar pump or any other sort of pump. So although the talk here has been, hey, there's quite a bit of potential here, sometimes when speaking to donors, it's the other way that I'll be saying, look, you're not able to just randomly get these high yields from basement rocks. So the fact that only a very small amount will be able to do more than 5 litres a second, I think will give some people have to rethink some of the strategies about how to get higher reticulated schemes built, that actually basement rocks might not be, or probably will not be able to supply a lot of them. So, Seifu, that's probably not a very neat answer, but I think we have to be clear on what we think basement aquifers might be able to supply. And it looks from this sort of work comfortably, maybe a bit of work, something about a litre a second, maybe a bit more that might be able to do that. Much more than that is going to be a lot more complicated.
Yeah, thank you so much, Alan, and for this excellent work, showing, regardless of the fact that basement aquifers are classified or often depicted as complex and heterogeneous and chaotic. I think it's not chaotic, there is some pattern in it. And then understanding that pattern, factoring climate, topography, and all those factors based on data has extremely, I would say, revolutionized the concepts that we have about basement aquifers, which will have significance for policy making and for decision taking, and also linking back to what Dan said yesterday. So with puts on the field, how can one move from, let's say, a low probability situation to a higher probability situation that requires field information, data, and evidence? There are some hands already up, and Emmanuel Chibuki. Please, I think you're on the panelist list. You can ask. Yeah, okay, go ahead.
Thank you, Alan, for the wonderful presentation. Actually, I have a different question regarding to the potential of these basement rocks for managed aquifer recharge. For example, where you have some not so much recharge, but good permeability and porosity for recharge. I mean, what is the potential? How good would they be for storing water and using for future purpose or something like that? It's just a different question from what you presented, but I'm just a bit curious on how possible it could be. Thank you.
That's a really great question, and quite a difficult one. Again, it depends for crystalline basement rocks. It depends very much on that kind of weathering profile. If you've got a lot of clay at the top, the way that the kind of fertilitic soil develops, then it can actually restrict downward recharge significantly. So that kind of managed aquifer recharge going through the top can be quite problematic. It's something that I think India's a little bit ahead at this, and certainly in India, we worked again with partners in peninsular India looking at the crystalline basement rocks and the impact of old kind of check dams and managed aquifer recharge there. And what was quite interesting there was that you did see an impact of managed aquifer recharge close to the check dam, but we didn't see any impacts regionally. So although it did cause it did help the borehole that was next to that check dam, it didn't actually improve the water much further away than that. So I think there's quite a bit of work to do in that. And that might be due to the connectivity of the aquifer, might be due to how much water can go in. But I think there's also a little bit of work, and sorry, I'm being too long with my answer, but there's a lot of work to do on actually natural recharge in basement rocks. Again, there's some work that we and others have been doing looking at how recharge in basement rocks changes when you start pumping. So I think there's quite a bit of work to do on just understanding natural processes of groundwater recharge in basement rocks and how that changes once you start to perturb the system by pumping.
Thanks so much, Alan. There are a few other questions. Let me give a chance to attendees. Maybe Prof. Goni. Prof. Goni also wrote the question.
Hello. Can you hear me?
Yes, clear.
Yeah, Alan, excellent and inspiring presentation. Thank you very much indeed. I'm just wondering in the Nigerian context now, basement aquifers, there's this deep aquifer, over 200 meters deep aquifer exploitation going on in Nigeria. What's your take, especially on sustainability, thinking about where could possibly recharge come to such a depth? And then you are comparing weathered fractures and as one option or tectonic. What are these weathered fractures? I thought they come with just the, do they lead to fracturing or are we looking at other possibility? But thanks a lot. And I'm happy at the end where you come to localize some of these activities. We'll be very interested to take it along. Thank you very much.
Thank you, Prof, and lovely to hear you, and great questions. The deep aquifer question is a really good one, and my experience has been that it's very rare for there to be a deep, high yielding borehole from basement rocks. So the work that we have done both in southern India and we did a little bit in Uganda with Mike is that deeper boreholes tended to have lower yields than shallow boreholes. It's probably because a driller kept on drilling, hoping they were going to get something. But drilling deeper rarely gives you a higher yield. There are the odd exception, and I think it's the odd exception then that drives this business forward. People looking for that deep groundwater, and there's some good examples in India around Bangalore where boreholes are they're drilling 300, 400 meters. Recharge, you're completely right. Where's the recharge coming from? Probably coming from shallow boreholes. It could be, now this is controversial, but it could be that a 400 meter deep borehole in basement rocks is just a nice storage tank. It's just a long, thin storage tank, and you're not getting a lot more fractures in water from the bottom. There's the odd occasion it might happen, but I think most of the time it's just storing water that's come from more shallow in the system. And
yeah.
Okay. Sorry, Seifu. Well, there was a second question.
Go ahead. Yeah, there is another question, another hand up from Edward, and then I'll go back to Aben later, Aben Berry. But Edward?
Yeah, thank you, Prof. So thanks, Prof. Alan, for a beautiful presentation. I really enjoyed it. Just to pick your thought on, again, the issue of sustainability and considering that most of these aquifers are coming from quite shallow wells. If I pick on the last answer you gave, the issue of contamination, what's your experience on that? Did you do some water quality stuffs also on these kind of aquifers across the continent? And what should we be doing? Because most of our population is very rural, and still we don't have this large infrastructure to supply us water, so we'll continue to depend on this. But yeah, so what's your observation, your take on the sustainability of this in terms of the water quality going forward as well?
Okay. Thank you, Edward. Again, a very insightful question. I think in terms of sustainability from recharge, it absolutely needs to be looked at. When you go from a hand pump to doubling or an order of magnitude greater yield for irrigation, you change everything. So in looking at the sustainability, we definitely need to look more at recharge and the spacing of boreholes. Good thing about basement rocks is that they tend to be slightly self-regulating because the permeability is quite low. The cone of depression doesn't go quite so wide. So in the the talk that I gave, I talked about aquifer length as being really important for high yields. That's basically the spacing between boreholes. So that really does need to be looked at, the recharge. And in terms of quality, yeah, we did some other work again with Seifu and Michael War and some colleagues in Malawi, where we looked at the water quality from a wide variety of rural boreholes, mainly in basement rocks. And yeah, I mean, looked at both from pathogens and from inorganic chemistry. So pathogens is, of course, still a problem in rural water supply boreholes, and I would say, and again, others might have a different view here, but I would say the main thing that needs to happen for improved water quality is standards in drilling and completion. That profile that I gave of the sort of permeability of the weathered basement, you'll see that it can be a very high permeability in the soil, in the ferrocrete and the ferrous soil. If that is not cased out, then that can shortcut this kind of aquifer kind of pathways, so you can get a lot of contamination going down the borehole along that kind of soil zone. So really good completion where that high permeability shallow soils are cased out is really fundamental for good water quality in the future.
So thank you so much, Alan. Now we have a couple of other questions, a lot of hands in 10 minutes. So you'll answer at least five questions in 10 minutes. And let me start with Aben Berry. Aben, maybe if you could introduce yourself quickly and then ask your question. Aben, please go ahead.
Thank you so much. Can you hear me?
Yes, we do.
I am Ebenezer from Ethiopia. Currently, I'm in Saudi Arabia. So, shall I continue my question?
Yes,
Dr.
please.
Seifu was my instructor, lecturer, and advisor. And so, thank you so much. I really appreciate for presenting such regional scale or continental scale hydrogeological work. So, when I continue to my question, it was you said Rigoli's thickness increase from gentle slope to one of the factors that affected slope, and the other is climate. So my point is, since this is true and evident, and your work is also continental scale, and how can these countries or Africa can work together to increase regolis from human intervention point of view? Natural thing which we can't control, but if they can work on sustainable climate and plan development work, is mostly some of the development work is going on is affecting or decreasing recharge. So is there any way we can advise policymakers or country level cooperation to increase recharge and sustain the environment that those people who live in such area can have sustainable water supply for drinking or even for their small-scale agriculture and like that? That's my question.
Thank you, Aben Berry, and then Alan.
Yep. Yeah. Thanks for the question. It's a very big question. I think cooperation between countries is so important in any kind of development work and in any kind of science. And I think the kind of stuff we're doing here, so what Seifu is doing, I think scientists and professionals working together across borders is often a very good way of enhancing that collaboration. There's also needs to be things done with the politicians, which are happening through AMCOW, through IGAD, through other SADC, GMI. There's lots of kind of ways that these things, cooperation is happening. But we as professionals and as scientists can also just increase our collaboration at our level and making sure that we are sharing information and sharing ideas. I think that's something that we can all do.
Yeah, thank you so much, Prof. Let me go to the questions in the chat box, many of them. And So a question from Moses Suta from Zimbabwe. Is there any current regional data looking into how basement aquifers could support higher extraction rates enabled by solar pumping without leading to over-abstraction and long-term depletion? And then from Vincent Casey from UK, I believe, thanks for the fantastic presentation, Alan. I agree that nothing beats field-based observation. Looking to the future, what would have to be in place in terms of monitoring for AI-based enhanced modeling to accurately predict, understand yield potential in real time? Additionally, what are the main barriers to this at the moment? And then another question from Gashaw Taspaw Chekol from Ethiopia. Thank you for your excellent and inspiring presentation, Prof. Alan. So what will be the fate of communities in the area of basement rocks? How can we help them as hydrogeologists? And then another one from Hassan Shube from Ethiopia. Thank you for your insightful presentation. The case of basement aquifers, rainfall controls the formation of thick regoliths. Would you please highlight the case of Ethiopian basement? I think it comes from the angle that climate didn't stay the same, over the last millions and billions of years, and then regolith formation might have been influenced by past climate, like the King surface in Cretaceous, Upper Cretaceous. So I think it comes from that angle. So a number of questions, Alan, before I go and open again for questions from the other parties.
Okay, thank you. And thank you for answering the last question, Seifu. That's good. Well, thanks for all these questions. Moses, been trying to get this kind of mapping together this kind of higher extraction rates. I suppose that's the kind of work we're trying to do at the moment, trying to develop that. We've also been working with a team of electrical engineers in Paris who are developing tools to look at solar pumping. So we published a couple of papers on that, and they've done some sort of codes which try and look at what kind of solar pumps might go where, related to the aquifer conditions, the recharge and overall exploitation, and the kind of solar energy. So there are kind of tools and methods that people are beginning to develop on that. Vinny, I mean, AI-based predictions. I think when we've been trying to do quite a lot of them at the moment. What it all boils for me, the most important thing is having data to train them on. I suppose that's why I talked about transmissivity data or yield data, that field data. If we want to have good AI models, we need to have really good in situ field data to actually train them. So the work that I was just explaining in the talk, we could only really look at the typologies where we had a really good data set of borehole yields or transmissivity and what the thickness of the regolith was and such like. So there's lots of methods out there. We're going to see more and more and more research and papers using AI. But when I read any of them, I always look at what's it trained on, what's it calibrated on. You can produce beautiful maps, wonderful maps of aquifer yield and potential, but actually what are they trained on? What are they? How reliable are they? So that would be my thing. Yeah. So it's bread and butter hydrogeology that we need to do more of.
And there was this from Hassan Shube on paleo, the role of past climate and past tectonics.
Yeah, absolutely. And I've had lots of discussions with our geologists about that. And you'll know about the kind of old African weathering surface. That was a historical surface. So historical climate, really important in developing basement. And we try to look into that a little bit. The weathering is probably some I know I'm not sure how old it is, but our geologists would say maybe some of the oldest weather might be 1 million years or so. So we're not probably having to look back climate, a huge distance into the past. But that historical climate and repeated kind of weathering is certainly important. Yeah.
Yeah, Just to reflect on what Hassan said, if you drill through in some places when the volcanics is thin, and if you drill through the volcanics in the highlands in Eastern Africa, you'd cross thick regoliths, so shielded from being stripped away by the uplifting. And then in places where it has to be sheltered, like in Eritrea and parts of Ethiopia, you could see hundreds of meters of regolith thickness. Hassan, it's just a reflection to Hassan. Okay, then go ahead, Alan.
I think it is. We see the same in Scotland here, where our basement is 2.5 billion years old, and you can still see some weathering in it that happened a long time ago that's been preserved. So you're right. What I presented is a very kind of simplistic way of looking at it, and there's lots more work to be done in this area to try and improve it. Yeah.
And then another chance to Chibuke.
Okay, thank you, Alan. Thank you so much for the presentation once again. So based on my work, we are looking at the global models, and there's this open question on how to better incorporate processes in the high mountain environment. This issue of local regional flow, mountain block and mountain front recharge. And also based on your analysis, you mentioned that you have lower probability of regolith developing in these high mountain regions. So based on your opinion, are you ruling out the fact that there might be sub-regional flow in the mountainous regions, like very deep flow in these regions, and basically you only have local flows because you have lower probability of fractures and regoliths based on the slope? Yeah, thank you.
Yeah, very good question, Chibuke. And well, it's a difficult one to answer. I think when we go to global models, when we've got grid squares of maybe 120 kilometers or so, it is one of the fundamental questions. Can we represent the system as a 1D system, or do we need to go to 2D or 3D? So for many hydrogeological environments, actually, regional flow is probably not occurring over that kind of 150 kilometers. So a lot of the shallow crystalline basement that we're thinking of here, flow paths are unlikely to be that long. So it might be that for our global models we can simplify and looking at them in 1D. However, as you rightly put, for sort of mountain systems, or you can have much longer flow paths. I mean, several people on the call here have worked on the regional flow from the Ethiopian highlands down into the rift. I mean, Seifu can tell us a lot about that. And there's these kind of much longer regional flow paths occurring. But it might be that we can simplify for a lot of environments and approximate as 1D flow. But the work needs to be done to try and understand the extent of regional flow in different aquifer types.
Yeah, thanks so much, Alan. Maybe quick reflection on the following two questions in the chat box. What kind of data would you require to train the AI model? And the other question is it worth the effort to use solar pump for farming if there is a coal mine and power station in South Africa? It's from South Africa by Gandhi. And then the other question was from Kunamwami. Okay.
Great questions. I mean, for the AI model, it depends what you're doing. If you're trying to, if we're talking about AI models for predicting borehole yield, then actually we need good yield data to train it on, yield data or transmissivity data. So that will, because you can put all the input data into the AI model, the digital elevation, the geology, shove all that in as the kind of predictors. But to know whether we think it's giving you the right answer or not, we need good information on where boreholes have high yields and low yields. So that really is a fundamental that we need to train to train models, is that good training output data set. And I mean, that's an interesting question on solar pumping. I take it that is it worth reducing the carbon for solar pumps? I think if you look at India, they predict about 5 to 7% of their whole carbon output is through pumping, through that groundwater pumping. So yeah, them changing to solar would make a big difference. I think with solar pumping, though, it's not just about the carbon, it's about the off-grid, which is so important for many parts of rural Africa. And it's being off-grid, it's possibly being cheaper running costs and such like. So if that's what the question was about the carbon, I think it's more than just the carbon for this kind of solar pumps.
Yeah, thank you so much, Alan. There was a question about if we are going to put this in YouTube and share it. Yeah, all the presentation, it's our intention to share it via IH webpage, and this will be available based on consent from the presenters, and we'll try to make it as soon as possible. And also, Alan, we are running out of time. I think this was very rich presentation, and then this reminded me, a hydrogeology map in one of the African countries, 1 to 2 million scale, and then if you go and see the legend of it, it says, all basement rocks are like regional aquicludes. Just finished. So regional aquicludes, but this in-depth studies of this sort could bring that to light and say it is not hopeless as a situation, and then there is high chance, given that sufficient investment in knowledge and data is put into it, this can further be understood at continental scale as well as at local scale, at various scales, to make use of this, better use of this aquifers for, the SDGs, and So thank you so much, Alan. Maybe one final question. From Dan Odero. Maybe this is last question. A project we did recently encountered water in fractures up to 280 meters below the ground. This is similar to the Ibrahim's earlier question. And then what are interpreted to be saturated subhorizontal fractures and fissures in otherwise compact basement rocks. But there was very good reason for the borehole being an exception in the broad rule. The borehole is located in estimated 4 to 5 kilometers into junction of pair of major fault zones in Great Rift Valley. And could pump 25 meter cube per hour.
Yeah, that's very insightful and very well put. You do get higher yields, but they are in these kind of specialist situations. Good observation.
Thank you so much, Alan. It was such an enriching presentation and discussion, and food for thought for all of us to make use of this kind of approaches for local level decision taking and siting of boreholes, and advices to policy. I really appreciate. And then Olivia, back to you for announcements about the next session, please. Thank you, Alan.
Thanks, everyone. That was a great session. We're going to have a 7-minute break now, a bit shorter than planned, and then we'll go to the next presenter after that.
So break for 7 minutes, and then we come back in 7 minutes. Okay, thank you so much.
Hello, is that visible?
Yeah, we can see. And thank you so much for stepping in last minute, Isaq.
Yeah, thank you so much. Yeah, so my name is Isaq Tuna. I'm a recent graduate from IHE Delft Institute for Water Education. I'm presenting about hydrological functioning of water pans based on insight from isotopes and hydrochemical analysis. This thesis, my thesis study that was done, and contributors from my mentors and supervisor, Dr. Constantina Katsano, Johan Winninger, and Ken, and Asha Ogon from Regional Center for Groundwater. They are all tuned in and listening. So my presentation will be on, I'll give the introduction, aims, and questions, look at the study area, the methodology, results and discussions, and implications and ongoing work. So, what are water pans? Water pans are small ephemeral water bodies that are found in mainly dryland areas and are mainly thought to be receiving surface runoff or intermittently refilled by rainfall. This makes water pans usually isolated from studies where we look at how groundwater interacts with surface water. And especially because they are also isolated hydrology system, most of the studies have not really concentrated on understanding what is coming in and what is going out, basically the water balance of these water pans. In Narok, water pans are very crucial water sources for livestock, for irrigation, especially for the pastoral community living there. And the Kenya National Masai Mara National Park, which is there with a lot of wildlife that really depend on these water sources, especially during dry periods. So these water pans are very important for especially in dryland areas, and those that contain groundwater is actually very important for climate resilience projects, because these are water pans that last longer duration post the precipitation periods. And these are important and can be a focus for climate resilience efforts. So I wanted to do this study, especially because they were limited study, and I wanted to bring out what is the hydrology of these and determine whether there's connectivity to groundwater. So my research aim was to use a multi-tracer approach. Why did I use this? Is because usually these small water bodies, it's hard to get satellite data that have a higher resolution that you can study them. This is one reason that isolated these water bodies from being studied that much. So my research question was to look at this hydrology, the water sources, evaporation, and groundwater connectivity. So my study area is in Narok County in Kenya, where we have high elevations on the northern part. This is around the Mau highlands, and on the southern part we have elevations dropping to 600 from 3,100. These are mostly hills and quartzitic kind of outcrops that come from this. The upper part is usually high at 3,000 because of Mau volcanic kind of highlands. Geology of this area is mostly the volcano on the northern, that is the volcanic kind of rocks, and on the southern where there's these hills, it's mostly of quartzitic kind of outcrops that comes from this area. The area on the northern part also, there's like these volcanic kind of ashes that are coming from the highland areas, and that is where it's mostly flat terrains. And this was mainly my criteria for selecting, okay, these water pans, the different geological settings and the different topography, to see whether we can have groundwater coming into these pans. So the study sites are located on this map. You can see water pans in blue. Several 39 sites were chosen for this study, including some springs and one borehole sample. It was difficult to get groundwater data in this area because there's essentially like a pastoralist area where they depend on this rainfall and surface runoff kind of water holes to gain water, and so the potential of groundwater being having inflows in these water systems is very important. So this was my study framework. I went to the field. I collected in situ data, temperature, ECDO, radon measurements of grab sampling of radon measurements, measurements of water pans depth to get the volume estimation, and getting samples from all the sites. And then in the laboratory, isotope analysis of oxygen 18 and deuterium, and hydrochemical analysis of major ions, cations, and trace elements. So the results of this was plotted in paper to see with each tracer, that is hydrochemistry, isotopes, and radon, what can give an indication of whether this has groundwater input or has mainly fresh derived rainfall. So one sample was also obtained as a control seawater sample, so that I can plot my samples along the rainwater seawater mixing line on the paper diagram. So from this, we can see from the rain sample, that is the rain end member to the sea, the water pans, which are now indicated as surface water, and boreholes and springs are indicated as groundwater of different kind of hydrochemical type, mainly influenced by kind of dilution or a fresh derived inflow of groundwater. So we see that there are some pans that are more enriched in calcium and bicarbonate, and there are some pans that are more going into chloride type, and they are more kind of mineralized. You can see on the scatter plot of calcium and sulfate and sodium and chloride along this rainwater mixing line. It plots close to the rainwater end members, so suggesting that these water sources mainly rainfall. Of course, the sea is far away from this, but different kind of grouping is observed depending on the extent of mineralization. So the first group, which is sodium, calcium, with some samples enriched in potassium, these groups are mainly the ones shown in light blue, and these ones were mostly indicators of freshly derived rainfall. Calcium and bicarbonate are usually indicators of new freshly derived meteoric waters, as compared to the more mineralized sodium, calcium, bicarbonate water pans. So we can see this also plotted a solar plot where we analyzed different kind of concentrations of which provided an indication of whether the low kind of mineralized pans were classified as rain-fed, and the ones with high mineralization, which were more of sodium bicarbonate type, were classified as more to contain groundwater. So this was mostly, you can see from the spatial distribution of the water types using stiff plots, that on the northwestern part near Narok area, we have we have water pans with the sodium, calcium, mostly bicarbonate water, which is more of the freshly derived rainfall, and these were mostly on the volcanic ash terrain, these kind of flat areas. Then on the southern, where we have this sodium bicarbonate, more mineralized water pans, the chemistry of the water pans mostly on these early outcrops. So this led to also to now look at exactly now each location between water pans and springs, then depending on this spatial variation, what are the chemical ionic profiles of this. So from this, we see like an area like Taie, we see spring 4, spring 5, water pan 17, water pan 18, which is in close proximity, have similar ionic profiles. The concentration of different ions actually rises or falls together. This suggests that there's some hydraulic connectivity between the springs and the water pans based on the chemistry. Similar to you can see the plot on the graph E, we see some springs and water pans showing similar profiles on this shoreline plot. So based on that, this kind of water pans were classified as groundwater fed baselines. So we went further ahead to look at now the isotopes, which would they indicate. Of course, stable isotopes provide an indication of water origin or water processes that the process that water has undergone. So based on this, I compared the local, the water pans to the global and local meteoric water lines. The local meteoric water lines was plotted here is from Kericho Station in Kenya, and it's more or less likely aligns with the global meteoric water line. Also, local evaporation line was plotted based on doing a regression of the water pan sample to see the deviations that usually indicates the extent of evaporative enrichment. So from these plots, we see that there are several water pans that show groundwater, and plot on the lower part with groundwater and samples, that is springs and boreholes. These water pans have an indication of groundwater input. Unlike some of the water pans that plot further on the local evaporation line, the slope of the evaporation line is also 5. You can see as much it shows that it is more accurately describes what happens in dryland area. So this kind of evaporative extent in water pans show that there are those that are primarily connected to groundwater system, and those that have no groundwater system and experience high evaporative enrichment. We went further to do grab samples of radon to analyze, to look for groundwater input. Radon is an important tracer for groundwater input to surface water. So depending, usually radon is 2 to 3 higher magnitude in surface, in groundwater than in surface water. So the concentration of radon can act as an indicator of this. So grab samples of radon were plotted here, and you can see from different water pans. The water pans that were on the northern part actually did not meet this threshold to classify them as groundwater dependent, and most on the south that were having some groundwater connectivity. You can see spring 9 and spring 8 here, for example, have higher radon because they are more from groundwater, and they have higher radon concentration because of the different rock water interactions that is there. So I went ahead to look at analyze a statistical analysis where from principal component analysis of the chemical ions to see if we can see the difference between water pans that are rain-fed and those that are groundwater-fed. And from this, we derived 4 principal components. The first and the second were the ones that explained more variations in the different water pans. The 2 components, the first principal component represents the mineralization axis, where where water pans that were having groundwater connection showed more, they had more principal component scores on this axis, that is suggests that they have more kind of mineralization from looking at the variables that are loaded on this principal component. The second principal component of aluminium and iron, this was an indicator of these feldspar kind of minerals that are derived from these volcanic ashes that were on these flat terrains in Narok. These are mainly minerals that are mobilized by surface runoff, and water pans that were rain-fed actually scored higher on this principal component axis. And this suggested that might be soil kind of surface runoff mobilized some soils and minerals into this water pan. So based on this,
my apologies, Isaac, for interrupting. Would you please conclude in a couple of minutes to keep up time?
Yes, thank you. So based on this, I developed a conceptual model of this interaction of water pans and groundwater in this study area. And we can see that mostly on these quartzitic hills is where they act as a recharge zone for shallow groundwater to move down hills as either overland flow where there's a springs, or where communities actually struck the water table close to this hill. So the future work of this is that I've installed several instruments to measure, to take weekly isotope samples between the dry and wet seasons, and also to measure the water level and take tritium analysis to further refine and get more studies. So this is important because of the implication on whether these water pans are groundwater dependent ecosystem, especially they provide water during this dry period, and the consideration of now looking at these water pans in an integrated water resources framework. Thank you.
Thank you so much, Isaq, for the interesting presentation. If you have questions for Isaq, please, you can take one or two.
A quick one.
Please,
It was an excellent, nice presentation. Very well done, Isaq. One question is about diffusive radon flux.
Yes.
And then how do you account for that in your future work? Some of this high radon level in the pans may be related to diffusion, not advective groundwater input. And is there any plan to?
Yes. So this now there's a plan now to go and do radon because this was more of a ground grab samples now to go and conduct in situ radon measurements at the site for a longer duration to do radon mass balance.
Okay, thank you.
Yes.
Okay, Prof. So I think it's better that we move to the next presentation. Olivia, would you please share Professor Ferguson, Grant Ferguson, Darcy's lecture?
Yeah, sure. Let me just get the video up now.
Thank you. Let's if there is any reflection on Prof. Grant Ferguson's presentation, this is the time.
Yes, Bahairu, let me break the ice. And I found the presentation very insightful and with a lot of implication to the hydrogeology, particularly in Northern Africa and Southern Africa. And there is a general perception, as he has highlighted, which we don't know where it comes from, saying that all groundwater or fossil groundwater is not sustainable or young and sustainable. So this is a simple approach and easy to communicate to policymakers. And so that perception is widely held. Grant and his colleagues try to add the various possible nuances to it, and it should not be taken lightly like that. And from his presentation, there is decoupling between hydraulics and age of groundwater or age of traces. So because they are not one and the same, age should not be interpreted as an indicator of sustainability very simply like that, unless the hydraulics and understanding how water flows and where did he take the samples from, and so without understanding how different flow lines converge, etc. So one example I saw was, if you pump a borehole which is returning old groundwater but adjacent to a river, by pumping it, eventually you will not deplete it because it is old, because there will be stream capture, and then that stream capture will change the age of the water as well as the age of the tracer, and then it will also eventually, doesn't mean that the borehole is going to run dry, but it's going to capture the stream. So I think the main tenet of this presentation is that age is not the same as hydraulics. So again, the message I take out of this is, moving forward in African hydrogeology, as much as possible, isotope-based studies, age studies must be coupled with hydraulics. Otherwise, it will not give us a full picture about how water flows and its sustainability, or relation between surface water and groundwater. What the implication of pumping old groundwater would mean, that it's going to be depletion, but it depends on the hydraulics around it. So I think that came at a very critical juncture, because this widely held perception between age and sustainability. So I recommend that this video be shared through the network, and for colleagues in Africa who haven't listened to this presentation. Thank you so much.
Thank you so much, Prof. Prof. Grant's Ferguson presentation was really insightful, and he brought some of the questions that we should ask ourselves again, because there are some perceived knowledge, but when we track to the depths of it, probably there is no that clear explanation why we have some knowledge about some of the things. Like we said, age is one of them, groundwater age, and it's really important presentation in a way that would encourage us to ask ourselves some of the things that we think we know. We need to scrutinize and look into in depth, so that we have something clearer than we used to have. Thank you for the reflection, Prof. If there is other reflection, we can take a couple before the lunch break. Edward, please go ahead.
Okay, thank you, and thanks, Prof, for the highlight. So I think a question I want to ask is, when we are using isotopes and chemistry alongside hydraulic measurements, should the focus be on understanding processes rather than fixating on how we quantify understanding flashes, and then also maybe we want to kind of do these estimates, but it looks like, for example, the age, since it's not something that you can easily put your finger on and say that because the age looks this way, then this water is not sustainable. Then should our attention be more on understanding what the systems look like? Is there mixing? Are these systems decoupled from each other? The traditional observations of the origin of, let's say, the water itself, and maybe some pollutants or maybe salinity, things like that. Should our attention be more on that? Are those things that we can say, for these ones, we are sure this is what is happening based on the fact that these are direct representation of the water molecules themselves, rather than moving into this big space of saying, okay, because this groundwater is giving us 5,000 year recharge signal, so this is not sustainable. But rather we have this idea of, okay, this aquifer maybe is sourcing its recharge from streams, or there is this interaction between these systems, things like that. Should our focus be more towards that, or we should still leave the room open to interpreting the ages, but just be a little bit cautious?
Thank you so much, Edward, for the reflection. Dan, please go ahead.
Thank you. Mine is a reflection on the hydraulics of aquifers. I'm thinking about multi-layered volcanic aquifers in Africa, like we have in Kenya, which are under high hydraulic gradients. And so what happens is the shallower aquifer layers in the suits get depleted with time, but then they still have groundwater in transit. And then we have boreholes being drilled deeper to tap deeper aquifers. And because of the high hydraulic gradient, then there would be a mixing of waters in terms of water quality. So we end up with poorer water quality. And then, of course, older waters mixing with younger waters. And then for the younger annually, or rather renewed water in shorter time, which is basically water in transit, drillers or geologists, hydrogeologists are tempted to screen these shallower zones, but then you end up with the yields that are not sustainable from these upper aquifers. So you may end up with the water that basically drops into the hole at pumping level, which then sometimes creates air bubbles that ends up in air entrainment in pumps. So you end up with the motors overheating, and burning up because of basically air entrainment. So I think that would be my reflection and lessons that we should learn in terms of younger waters mixing with the older waters. You get poorer water quality, and then trying to tap depleted aquifers, then you end up with the electromechanical problems in your boreholes. Thank you.
Thank you, Dan. I just heard that Majid is ready to present before lunch break. So Majid, if you are ready, would you share your screen? Yeah, this should be perfect. So Majid, you have 15 minutes. Please try to keep up the time. You can start.
Okay, thank you very much, first of all, for organizing such an interesting conference. So the research that I will present, some of that would be about the assessment of spatiotemporal variability of groundwater recharge across Chongwe River catchment in Zambia. So this is the motivation of this research is based on the SASCAL project. Indeed, the overarching objective of SASCAL project is improving food security by integrating climate resilient crop into maize-based farming systems among smallholder farmers in Zambia and Namibia. To that respect, we need to do some simulation regarding the hydrological components, and as a result, we need to estimate the groundwater recharge. So the specific objective of this research is hydrological modeling at catchment scale using the SWOT and water assessment tools, SWOT Plus indeed. And based on that, we simulate different water components, including groundwater recharge. After calibration and validation of the model, we are supposed to test several climate change scenarios and crop types for coping with water management issues in face of climate change. So, as you know, the SWOT is the SWOT model is a quasi-distributed hydrological model, and based on which we can simulate the different water components at catchment scale, and based on the integration of the hydrological, climatological data and management practices, we can set up the model, and the output of the model would be surface runoff, groundwater flow, erosion, nutrient transfer, soil moisture, and etc. To that respect, we have started collecting the data, including the climate data, such as precipitation, temperature, relative humidity, digital elevation model based on SRTM satellite with 30 meters resolution, and global soil data, which was extracted based on some pedotransfer of using artificial neural network, and land use land cover map based on the Sentinel-2 with 10 meters resolution. In addition to that, I had a very productive field work and in Zambia recently, and based on which I could collect a very nice data from commercial and local scale farmers with the support of WARMA, Water Resources Management Authority in Zambia. And I could also collect asymmetrical discharge for some hydrometric station for the calibration of the model. And you see that the SWOT has different inputs, including the precipitation, temperature, wind speed, solar radiation, land use, soil, and topography, and as I said, different outputs like runoff, soil erosion, water quality, at different temporal resolution, daily, monthly, and yearly. So I have also collected most of these climatic data from global data source, especially Water iTech, which was very helpful, and I highly recommend it for those who want to use the SWOT model, because the data is formatted based on the requirement of the SWOT model. So application area is Chongwe River catchment, which covers some part of the capital of Zambia, which is Lusaka. And we could have some 5 hydrometric stations, but unfortunately, the rest of I would say the half of the catchment, we have no hydrometric station because a national park covers most the downstream of the catchment, and it's not possible to install a hydrometric station and to monitor the stream flow discharge. So it is around 5,000 square kilometers, and the major land use is agriculture, built-up areas, forest, rangeland, and shrublands, and around more than 800,000 people live in this catchment. So for the simulation of the hydrological component, we have the data set from 1976 to 2022, out of which we consider 3 years for spin-up period or warm-up period from 1976 to 1978, and and the calibration subset is from 1979 to 2010, and validation from 2011 to 2022. So here you see the digital elevation model, and in the left side and the right side the land use. So the elevation is too small. I think it's from 358 to 1,464, and you see the downstream of the catchment is where the Chongwe River joined to the Zambezi River, which is a very large river between the Zambia and Zimbabwe. And in the right side, you see the land use of the catchment area. And as you see, the rangeland and cropland are the major land covers of this area. And this red area is the built-up area, and where the Lusaka is located. So, as I said, I'm still in the phase of calibrating the model. So the result that I will present here, it's based on the calibration phase or subset, which span from 1979 to 2010. As you see that this is the average of annual diffuse and concentrated groundwater recharge across the catchment, and you see that the major part of the catchment, the groundwater recharge is from 188 to 1,000 millimeters, and in some part, which is we have a very high concentrated groundwater recharge, especially in the downstream of the catchment. So we found that in the simulation period, in 2002, we had a very severe drought condition with a precipitation amounting to 700 millimeters. So as you see that we have very low diffuse groundwater recharge over the Lusaka and built-up area. And as a consequence, we have also less concentrated groundwater recharge. Similarly, we wanted to make a comparison between the very severe drought condition with a very wet year condition, which happened in 2007 with more than 1,400 millimeters precipitation. And so the diffuse and the concentrated groundwater recharge is much higher as expected. As one of the output of the SWOT model, because the soil water is a very important parameter both for agriculture and also as a proxy for estimation of groundwater recharge. So we simulated the soil water also across the catchment, and you see that it varies from 2 millimeters to more than 600 millimeters. So for the simulation period of 1979 to 2010. And we tried to make some comparison between precipitation and groundwater recharge. As you see that the groundwater recharge is almost 20% of the total precipitation. So we try to make this comparison again between the groundwater recharge and actual evapotranspiration. So it's probably hard to say that there is a strong relationship, but we can see a very good relationship between soil water and groundwater recharge. And a relationship between water yield and groundwater recharge. The water yield here is a combination of surface runoff, groundwater inflow, or base flow, and finally subsurface flow or interflow. And it's hard to say that we have a good relationship. That's why the conclusion part is based on these results so far, because as I said, the model has not been calibrated so far, so it's in the calibration phase. But I would say that soil water can be probably a better calibration target than classical stream flow discharge. And as we have a very good data set of soil moisture data based on remote sensing product, so we can consider it, especially for the downstream of the catchment where we have no stream flow discharge. And one of the flaws or shortcomings of the SWOT model is oversimplification of the groundwater domain of the modeling area. That's why we recommend to couple SWOT plus with a groundwater flow model, probably MOT flow, which is the most commonly used model for this purpose. Thank you very much for listening to this presentation.
Thank you very much, Majid, for the excellent presentation. Any question for Majid? Let's take a couple of questions. I don't see any question in the Q&A. So if you have any question for Majid, please. It was clear, Majid. Nobody is asking you.
Great.
Thank you so much.
Thank you very much.
So I still remind you to fill in the survey. Those of you who haven't filled the survey, please do. I think this is time for lunch break, but before that, I will give the chance for Olivia to say, what time should we rejoin?
We can return at 2 o'clock as planned. We can just have a slightly extended lunch break. I'll just take this time to remind everyone to please fill in the survey as well. I've put it in the chat box, so if you have a bit of time, we'd be really appreciative of that. Hi, Edward. So we're back. Are you ready to start hosting?
I think so.
Great.
Hi, everybody. Welcome back. I think we'll continue with the presentations. I think we have 7 presentations in all. And we will ask presenters to stick to the time, 12 minutes of presentations, and then we will have 3 minutes of questioning. So Tesfa will share on managed aquifer recharge potential mapping in semi-arid mountainous terrains of the Tigray region in Ethiopia. So Tesfa, if you are ready, please share your screen and then over to you.
Okay. Thank you. Thank you very much for giving me this opportunity to present my work in this very prestigious Congress. So my work, my presentation will focus on managed aquifer recharge in a small catchment in northern Ethiopia. My presentation is based on a research work carried out by a group of researchers from Ethiopia at Mekelle University and from Belgium at Ghent University. So the co-authors are as presented, as listed in the first slide. So my presentation will cover the seven parts. I will talk about introduction, objective, study area description, literature review, methods, and results and conclusions. To just mention some points about the concept of managed aquifer recharge. It's a means of sustainable water resource management. It's a mechanism of sustaining groundwater through an intentional augmentation of groundwater resource that is capturing and redirecting surface water or storm water into the aquifers so that it will be used in the time of need, like for example in the dry season. So this concept is increasingly vital in addressing water scarcity, groundwater resilience, in controlling saltwater intrusion, especially in coastal areas, and maintaining minimum flow levels, and also maintaining the sustainability of wetlands, and also enhancing and protecting water quality. So the current status and challenges, as we can see in several literatures, that the concept is growing its application or its adoption in many parts of the globe. So the popularity of managed aquifer recharge is increasing worldwide. There is also an enhancement of the research and monitoring or supporting the application of the managed aquifer recharge. But still there are also challenges related to technical issues in applying managed aquifer recharge, cost associated with implementation, and also risk of contamination, especially if there is no careful application of this concept through water quality assurance. So the procedures and methodologies of MAR has been well established. Like the groundwater assessment is necessary, and hydrogeological assessment of the area where you apply. The hydrology and water resource should be evaluated, its availability, quality, and seasonality. And environmental and land use considerations should also be taken into consideration during the application. Water quality and contamination risk assessment should be taken into consideration. Geophysical and geotechnical survey of the area is also necessary. Feasibility and cost analysis are also important. And in addition to this, people have been applying different types of models and simulation using GIS, MCDA, and the like, in order to evaluate the feasibility of application of managed aquifer recharge in different parts of the globe. There are best practices around the globe. The first mentioned is Australia, USA, and in Africa, especially South Africa is commonly mentioned in applying managed aquifer recharge concepts. Specifically, in Australia and California are commonly mentioned in the literature in successful application of managed aquifer recharge. Coming to Africa, not so extensively studied, but some studies indicate that over 80% of Africa is moderately to highly suitable for managed aquifer recharge, according to Ibrahim et al., who has done several publications on the managed aquifer recharge in Africa. The same authors also have reviewed the application of managed aquifer recharge in Africa in different countries. As you can see in the graph, they have found out that the most successful country in applying managed aquifer recharge is South Africa, next Tanzania, Tunisia, Kenya, Algeria, and the like. Ethiopia, as you can see, is among the list in the African countries in applying managed aquifer recharge. I have tried also to review the research carried out in Ethiopia in relation to the managed aquifer recharge. There are not much work, but few research and also some development activities are being carried out. The prominent one we have found is by Yosef et al., managed aquifer recharge suitability mapping in Drought catchment in Ethiopia. That there are still some research work, some MSc work and the like, but not much advanced as it is observed in other parts of the globe. So coming to the study area, we have tried to apply managed aquifer recharge in a small catchment in northern Ethiopia. This catchment is located in the Tigray regional state that is located in northern Ethiopia. This catchment covers around 470 kilometers square with an elevation of 1,400 up to 2,800 meters above sea level. In the area, the precipitation ranges from 662 up to 690 millimeter. The area is a semi-arid area where there is a serious shortage of water due to unbalanced or spatially and temporally variable condition. In the area, rain is expected between July and August. In these 2 months, in many of the cases, these 2 months even are not, the area is not receiving sufficient water. So the area is drought prone, a very highly affected area, degraded area. And in this area, we want to see if there is a possibility of applying managed aquifer recharge. Here, the meteorology and hydrology of the area we have assessed based on field assessment in the area. We have tried to characterize in terms of the drainage condition, the precipitation condition, the topography of the area, the slope of the area we have also generated. And we have assessed the geology, or we have based on a small-scale geological map. We have done field surveys and we have generated the geological map in the area. As is presented in the slide, the geology in the area ranges from small patches of alluvial deposits up to the basement rocks, where we have metasediments and metavolcanics as well as granites in the area. We have sandstone, both Adigra sandstone and...
Tesfa, you have less than 5 minutes, please. Let's make progress.
Okay, great. I will go faster. Okay. So we have also generated the land use land cover map of the area from the Landsat image. So now the objective is to assess the suitability of the area for managed aquifer recharge. So we have surveyed the literature and we have tried to see which of the thematic areas are most prominent or most influential in the literature. So we have surveyed this. The data sources, field data, remote sensing, and secondary data are the main ones. The methods we have followed is field-based assessment, field-based data collection, digital data gathering from the internet, from different databases, and then we have applied AHP-based MCDA in groundwater in GIS environment. We have also verified based on existing water wells, and sensitivity analysis has also been carried out on the model. So these are the thematic maps that we have used to generate the suitability of the area for managed aquifer recharge. So finally, what we have done is the managed aquifer recharge suitability of the map. The area has been generated using this relationship between the different thematic layers by assigning different weights and factors. So the result here indicates that in the area, about 40% of the area is found to be highly and very highly suitable for managed aquifer recharge application. The remaining is low, very low, and moderate. We have tried to verify the results of the model based on existing water points. These are shallow wells where groundwater has been found. So in this area, the groundwater recharge is local. So that means in these areas where we have the productive wells, the recharge is possible. So 73% of the water points have confirmed with the moderate to high suitability classes. So only 27% lie or fall on the low suitability. So that means our model is verified sufficiently. And then sensitivity analysis has also been carried out based on map removal of the different thematic layers. And according to this analysis, we have found out that none of the thematic layers are significantly sensitive, or the model is not significantly sensitive to any one of these. Relatively, they have a balanced mean variation index. So only the lower ones, drainage density and precipitation, are less influential, or the model is less sensitive to these parameters. So the conclusion, MAP can be successfully applied in our study area in the arid catchment. More than 40% of the catchment is highly suitable, very high anyhow, suitable, and spreading and percolation dams are recommended in the area for application. So we acknowledge our financiers and our collaborators, Bilirius, the Belgian government, the Ghent University, Mali University, and the Waradas in the study area who have been supporting us during our field work. Here are the references. Thank you very much.
Thank you, Tesfamichael, for keeping to the time. You made it. Yeah, so colleagues, the floor is now open if anyone has any question. Let me see, I think there's a question here. No, it's a good work. Okay. Please, if any, we have time for questions. If you have any question, okay. Okay.
Hello, can I continue?
No, yeah, Prof,
Hello?
please go ahead.
Yeah, this is Ebenezer.
Okay. Oh, Ebenezer. Okay.
Yes.
Eben, yeah, go ahead.
Yeah.
Please.
So thank you, Tesfamichael, for presenting Northern Ethiopia, Tigray, Majid Aquifer possibility. Given the presentation and the sensitivity factors, and to make it practical, and what to do, how we can implement a managed aquifer system, who will do it, and how to do it, and what are the best methodology to implement and see results. Is there any case study that we have done this managed aquifer work in northern Tigray or in Tigray, and we have seen results? And so my point is that so that we make it practical in northern Tigray. In Tigray, basically, water is one of the stressed region. So how we can make it practical? That's my point.
Okay, that's fine.
Okay, yeah. Thank you very much for the question. Yeah, it's the critical part, that is application. Research-based application attempts are there in Tigray in some parts, and at the Taie area, for example, in near Tembel, Abiy, research-based activities has been there, especially based on sand dams. They have been trying to implement managed aquifer recharge, but not extensively applied. It is going to be the first of its kind if we apply it. Last time we had a workshop here of the project, and all the stakeholders, both NGOs and governmental organizations, have been invited, and they have participated. And yeah, the same question they have asked, and during the implementation, we have to go to a small area, and large-scale investigation should be further carried out. This is kind of regional study. So when we apply it, we have to go for. But this study will narrow our investigation area from now on. We can go to the potential areas and further analyze it. And the main methods we intend to apply is the spreading method. Spreading, and also on the channel modification. Channel modification can also be very, very effective. As you said, the area is very water stressed area, very limited rain during a very short period of time. So this flood water can easily be diverted to recharge basins and then use it for the dry period. But it is, as its initial stage, I think it needs a lot of work. Thank you.
Thank you, Tesfa. I think there's another hand up. Ababe, right? Abebao. If you want to ask your question, unmute yourself and ask. Okay. Okay. Well, yeah. So just a quick question. So
yes.
these are okay.
Yeah, I have one question, Professor.
Yeah, go ahead, please. Go ahead.
Okay, thank
I'll
you very
follow
much.
up after. Yeah.
Okay. Thank you, Tesfamichael, for your nice presentation. I have one question for you. It is a critical research title, especially in the northern part of Ethiopia, which is a very sensitive area regarding the groundwater potential zone assessment. So my question for you is that how to see the contribution of geology in MAR or in assessing the groundwater potential zones in your study area, because most of the northern part of Ethiopia and dominantly in Tigray, the geology is more of the metamorphic rocks, and these metamorphic rocks are have the very low amount of groundwater potential and occurrence. So how to see the contribution of these geological materials in managed aquifer recharge? This is the question I have for you. Thank you.
Thank you. Tesfa?
Okay, thank you, Dalkacho, very much. Yeah, you are right. The geology has significant influence in managing in groundwater recharge. In our area, it's not only basement rock. We have also sandstones. We have also dolerites. We have limestone and also shale. So because of that, the geological materials have significant contribution, because there is high contrast between in areas where you have sandstone, you may expect high potential of recharge, and you have also shale where you have very low potential for recharge. Even the dolerite, unless in otherwise they are weathered and fractured in the top part, in some part, they are less important. So because of this, the geology is also given a high weight in the analysis of the AHP. So you are right, geology is very important, but this entire area is not basement rock. Basement rock, around 30% of the area is basement rock. The remaining is sandstone, limestone, and other rocks. Thank you.
Yeah, Tesfamichael, thank you. Because as you know, especially from your sensitivity analysis, I hope that the geology may be the most sensitive parameter for your work.
In my presentation, I have tried to show that there is no really dominant theme in the area. More or less, there are 2 point something. The mean index is about 2.3, 2.4, something like that. And except the low sensitive themes like the drainage density and the precipitation, which are not variable across the area. More or less, they are the same. So, but the remaining land is also very important in the area. Soil texture is also very important. These things and the topographic wetness index. These parameters, as well as the geology, they have nearly similar influence. So, well, it starts from the weight assignment in the process of the weighted analysis. So, yeah, it depends on how you start it. But you are right, the geology is very important, among them very important. But there is no significantly important or separately very important theme is not indicated in our case.
Yeah. Okay. Yeah. Well, Tesfa, I have 2 more questions for you, and then we will move to the next presenter. So one is asking how this study can be replicated in the Sahel region, at least to identify suitable zones for groundwater recharge. The other one is looking at your presentation and asking, commending you for a good presentation and then the approach. But there's a concern about the fact that you only taking into consideration surface factors, and you did not include issues of water table and, let's say, conductivity and all of that. Hydraulic conductivity, I guess that's the case there into this. So how do you plan to probably account for some of these things? And maybe my follow-up on that also is, in the area, perhaps you have some agricultural activities going on. And in mapping up this environment, I think it's important to also map them up in such a way that people who will be implementing some of these policies, which are very important, will know where to cite the areas that they should be implementing some of these, because you may be harvesting rainwater runoff, or maybe things like that, to kind of do some of these things. So how you plan to take or let policymakers know that even though these areas may show potential, if we go by that, we may endanger the water quality, things like that to consider. If you want to just look at those two questions, and then we'll conclude there. So one is how you can replicate it in the Sahel, and then the other one, how you plan to take into account subsurface, and if you do, what will be the effect on the model, the outputs that you have?
Yes. Okay. Thank you. Thank you very much. For the Sahel area, this is a small area where we try to exercise the application of the analytic hierarchical process in GIS using multi-criteria decision analysis. And the criteria that we have taken into consideration are only superficial ones. You are right. We are thinking about it. When we apply it in a smaller area for the application, we will take into consideration transmissivity, hydraulic conductivity, and the like for a better evaluation. But for now, the area is a remote area. The water points that I have indicated in the map are shallow wells only. In most of the cases, shallow wells do not have this hydraulic conductivity assessment. They do not carry out this assessment. So usually we have the water table during the drilling. So that's what we have. We could not have this kind of data. That's why we have not included. But obviously you are right. We have to take into consideration subsurface conditions for the future. For when we try to implement it, we have to further. Yeah.
Okay. Thank you. And then perhaps we'll take the last one. Piet wanted to ask you a question, and I want to hear it. So hear him. So Piet, please go ahead.
Thanks. Thank you, Chair. Yeah, that's a very important point that you just asked, and I want to follow up. But my question to you, Tesfa, is have you considered the storage potential, for example, the issues of leakage from one aquifer to the other? Because I think it's one important part of MA that you don't want to store water and lose it. So how would you want to consider that in your work? Thank you.
Thank you, Piet.
Okay. Thank you very much. Another very important question to be considered for our future research. In this case, we did not consider the storage factor. We just considered only the superficial conditions that are convenient for recharge enhancement. So based on how much recharge can we have in a certain area, based on the factors like slope, land use, land cover, geology, and the like, this is only recharge enhancement. That's what we have taken into consideration. But this is important point that we have taken into consideration for the future. Thank you very much.
Thank you so much, Tesfa, and thank you all. I think we will make progress. So, Phori, you can share your slide.
Oh, okay. Let me just share.
Thank you. So Phori will be presenting on groundwater exploration for drought relief in Mafenten, Lesotho. Phori, the floor is yours if you are able to share your slide.
Okay, let me just find to share. I'm going to PowerPoint mode. Let me just do that. Okay.
Yeah, please go ahead.
Thank you, everyone. Good afternoon, ladies and gentlemen. My name is Thabang Phori. It is really an honor to present to the first Pan-African Congress, Hydrogeological Congress, under the theme Hydrogeology in Time-Changing Environments. My presentation will focus on groundwater exploration for drought relief in Mafeteng, Lesotho. It will be highlighting a government-led response to pressing challenges of climate-induced water security. On the cover page, I have my colleagues from the water utilities, the urban utility as well as the rural utility. So my outline is as follows. It's the introduction, the background, methodology, the findings, then conclusions and recommendations. Lesotho is a very small country in the Southern Africa. Here it is. It's in the Southern Africa with a population of around 2.1 million people. It houses the source of the transboundary Orange Sinku River. And the country has a temperate climate with distinctive summer and winter seasons. The study area as mentioned is Mafeteng. It is the semi-arid of the lowlands of Lesotho. The study area is highly vulnerable to drought due to climate impacts, including the extreme heat, irregular rainfall patterns, the increasing water demand, and the depleting water resources. On the picture here, we have the earth dam, whereby the urban water utility was drawing water from. And this part where the mouse is, let me just do the point. It is where the water was being drawn before, but now the water has moved to this area. So it means now the trench has to be done so that water can move from that place to here. So looking at the varying climate, we are experiencing severe droughts and they are affecting the water security. Therefore, the government initiated a program whereby groundwater was being explored so that we can have alternative water supply. The objective of the case study or the study is to explore groundwater resources through borehole drilling and then to supply the vulnerable communities with sustainable water resources. Moving into the approach that we took, we did the assessment and the water supply to address the first objective and the second objective. The assessments that were done, it is the hydrogeological survey, the borehole drilling, as well as the pumping test to look at the flow characteristics of the area. And then we have the water supply, and in the water supply, after drilling the boreholes, the water utility in the urban areas, that is water and sewage company, will adopt the boreholes and connect to the existing reticulation to supplement the source of water, due to the fact that we are having depleted water levels in our reservoirs. As for the Department of Rural Water Affairs, which is the utility or the department in charge of rural areas, it is in a process of designing water supply systems and construction of the reticulation system to attend to the communities that are in need. I will just play a video of the video that I just played was showing the drilling rig that we use, the system that we use in terms of drilling and exploration
as a department. This is the down the hole percussion drilling. Now, going into the findings or the results, 8 out of 9 successful boreholes are drilled along the dolerite dikes, except one borehole that is along the matrix. This is the borehole that is along the matrix. And the green lines are the dolerite dikes. So one other thing that we used was to get the historical knowledge from the communities on areas that the old boreholes that have been drilled within the villages, and where are they in areas where we could not have visible dolerite dikes, maybe on the maps or even on Google Earth. Yes. Moving into the pumping test, we have 9 boreholes that have been pump tested within the district or the study area, and these boreholes will benefit approximately 4,000 people once the systems are in place. This is a summary that shows different boreholes, the depth of the boreholes, the different water strikes, the sustainable yield that was obtained from the flow characterization, as well as the remarks that were made after analyzing the pumping test. So only one borehole was not considered to be included for the water supply due to the low sustainable yield. This is the borehole. And it must be noted that the sustainable yield is not the recommended pumping rate or pumping yield. So the pumping rate will be dependent on the time that we are pumping, as well as the volume that will be abstracting from the individual boreholes. And all the recommendations for the pumping rate were developed to protect our main water strikes. Moving into the conclusions and recommendations. From this work, it is important, the important lessons that we found were that the surface water bodies are highly affected by climate variability, with Mafeteng being an area that is semi-arid, and it is clear that surface groundwater can come in handy to complement water supply to augment the deficiency that is experienced in the district. The other thing is that we need more groundwater exploration so that we can have knowledge about our characteristics, water characteristics. We also need to implement the integrated catchment management so that we can limit soil erosion. This is being highlighted because this is a reservoir that was constructed for a water supply for the town, Mafeteng town, and due to erosion and poor land management, the reservoir has silted and it has filled up, so the capacity of the reservoir has lowered. These features here are the trenches that were dug to channel the water to the pumping location here. So the water is now, this part, that's where the water is. And the entire reservoir has been filled up with silt. Therefore, the catchment management is important in higher lying areas so that the silt doesn't fill up our reservoir. Sorry. Also, the country has advised or has come up with plans to dredge, take out all the silt that is in the reservoir so that we can increase the capacity of the reservoir. But that is a long-term intervention, while the drilling of boreholes, it is a short-term to address the need that we are experiencing currently. With all that said, I would like to thank you for your attention and indicate that some of this is a case study that shows how government-led initiatives where coordination is being done can yield good results to serve the community and the population at large. Thank you very much.
Thank you so much, Phori. I think what is impressive about your work was the fact that this is coming directly from government. It's not coming from the university or coming from academia, basically, but from government. So this is really commendable. And thank you so much for coming. I think we have room for some questions. So the floor is open. Yeah, Piet.
Thank you, Chair. And thank you, Thabang, from Botswana, your neighbor there. Yeah. I'm just curious because I think this, as the Chair said, this is a very good initiative by the government. But I would like you, because when I look at your results, 8 out of 9 boreholes were successfully explored, but you have not shared in detail the exploration methods that you used. Would you like to touch on that? Thank you.
Okay.
Yeah, for it.
Can I respond, or I should wait for the second question?
Please go ahead. Thank you.
Thank you, Pete, for the good question. I did not touch on the methods, but in terms of survey, we were using the resistivity method, the vertical electric sounding. But the one that we were using is the Schlumberger array, whereby the poles that are outside are the ones that are increasing the size, but the electrodes that are in the center are not moving. We were using that one because it's time efficient as compared to the veneer, whereby the sounding goes across. So to complement also that, we were doing engagements to the community, whereby there are previously drilled boreholes, and we would look at the locations where they are, and then the geology of the area, how the boreholes were performing. We used that. That is in terms of survey. In terms of drilling, I indicated that we are using the down the hole drilling, which uses a compression. And then in terms of pumping test in our assessments, we were using the flow characterization, the FC, but also it had a touch of I can say experience to say how is the borehole, how are the drawdowns, and complementing it with the water strikes to say which level is the safe zone. And most of our pumping tests were 15 hours using for constant rating and then a recovery. Some were around 22 hours and then a constant for constant pumping and then a recovery. So we would look at how long it took to get to the water strike and beyond the water strike, and to compute, comparing with the FC, to say, does the FC really recommend a good, a better pumping rate? Now it goes back to my statement when I was saying the sustainable rate, it is not the pumping rate. So for the abstractions in the water supply and how to design a water supply, we do it 12-hour pumping, or we can do it at a 3, 4, or 4 hours pumping and allow it to recover. But if we use a lower pumping rate, we extend the time because we compute and we're aware that the drawdown will not get to the critical zone that is close to our main water strike. Thank you.
Thank you, Phori. I think we will make progress. I had one question to ask you about the water quality and your plans for sustainability of this water supply. So basically, maybe something you can, I know the water quality, you've done it already. You just didn't talk about it. But
yes,
your plans for sustainability of these very aquifers going forward.
Or the sustainability for a long run is advised by the pumping rate that we have advised, and we are looking at regularly doing the pumping test so that we are aware that the sustainable yield, we are still in the same range. And for the water utility company, more especially for urban areas, they chlorinate the water before taking it to the communities. But now, since we had some engagements with the communities, we made an outreach to inform them that around the boreholes, the land use must be protected so that there is no contamination or the subsurface contamination that can seep into our groundwater through the boreholes. Thank you very much.
Thank you. Yeah, I think we'll move to the next. Thank you so much, Phori, for that presentation. Very insightful. We go to Abebel. Abebel, are you here?
I'm hearing you.
Yeah, please. So Abebel will be presenting on spatial analysis of groundwater potential using remote sensing and GIS-based multi-criteria decision analysis method. It's coming from Ethiopia, the Blue Nile Basin. Please, the floor is yours. We can see your screen. Thank you.
Okay. Is it visible, my screen?
Yes, please. We can see your screen. Proceed.
Okay. Thank you very much. Good morning, good afternoon, and good evening, all the panelists and participants for the first Pan-African Hydrogeology Congress. And thank you to give me this chance to present my research finding. The presentation title is Special Analysis of Groundwater Potential using Remote Sensing and GIS-based multi-criteria decision analysis method in the Vietnamese catchment, which is part of the Blue Nile Basin. And this finding is within the my colleagues from Bahar University. And my presentation outline includes the introduction, area description, and the methodology, which is dominantly of the multi-criteria decision analysis method. And finally, I'll present the result and discussion part of this finding. And in the last, we have conclusion and the recommendation parts. When we start from the Okay, in general, from the world water resource, as you know, from the 100% of the world water resource, dominantly the 97% of the water is covered by saline, and the remaining 3% of the water is covered by fresh water. And among the 3% of the fresh water, dominantly, mainly for the 69 up to 70% of the water or the fresh water is dominated by the glaciers and snows. And 30% of the water is covered by the groundwater, and the remaining 1% of the water is covered by some surface waters and as a soil moisture. And we know that groundwater is a scarce resource, and locating or finding the potential zone and analyzing its quality and quantity of the groundwater resources. It is now the current issue. And according to the WHO in 2050, as we know, 5 billion people in the world, they cannot have an access to safe drinking of waters. And as you know, groundwater is a hidden treasure, and it is very difficult to find the potential sites. But nowadays, there is a variety of methods have been applied for assessing the groundwater potential zones. Among these groundwater potential zones, for identifying, there is some conventional methods like groundwater, ground survey, geophysical, and geoelectrical technique methods. But these conventional methods are time-consuming and very expensive, as well as they are complicated to implement these methods. However, currently the remote sensing and the geospatial technologies are the most successful, advanced, and easier methods to find the potential zone of a certain area. And nowadays, due to the uncontrolled and mismanagement of wastes, and also the presence of urbanization, global warming, and the increment of people in an alarming rate, as well as the uncontrolled industrial wastes, have some of the factors or the causes to analyze the groundwater potential as well as both qualities. And the groundwater demand by now is much greater than the supply. This makes the resource, or the groundwater resource, is very a scarce resource. And here is a statement of problem of this research findings. We have found three main statement of problems. The first one is there is a significant decrease of well discharges. There is a lack of enough boreholes that can feed the people's demand, as well as there is some boreholes which are non-functional due to the insufficient yields. So what is next is how we can demarcate, or how we can delineate the groundwater potential zone using the remote sensing and geospatial methods or techniques, especially in the upper Blue Nile Basin, which is part of the Fata Misr. And also here we have some specific objectives in these research findings. The first one is preparing of the thematic layers. I try to prepare 9 thematic layers, and also to locate the zone of recharge and discharge and groundwater flow direction, as well as finally I try to identify and delineate the groundwater potential zones using the geospatial methods. And the other is a research question, and also the relevance of this research is very important as a key input for there is some industry parks in the study area, which is the Bure Integrated Agro-Industry Park. And also this research also very important or relevant to the government and private sectors for assessing or for locating of the good potential sites to fill their demands, as well as it's very important for sustainable and effective planning of the groundwater resource management practices, as well as if there is a sufficient groundwater resource areas, it is very important for agricultural resource developmental activities. Here is the study area of, here is my study area, or its location. It is located in the Blue Nile Basin and in some part of the Fata Misr catchments, and geographically it is located 27023 to 32263 easting, and 1154,966 to 1206,716 north, and the total area coverage of the study area was 991 square kilometers. And the method for this work was multi-criteria decision analysis method. We have the primary and secondary data. From the primary data, I have tried to use the data elevation model to prepare the thematic layers like elevation, slope, and range density. And also I have used satellite images like Landsat 8 to prepare the land use land cover map and DVI maps, as well as from the secondary maps, I have used geological maps, soil, and the geomorphological maps, as well as there is some field observation data like water level and the yield measurements to validate the results. And first, I try to prepare these thematic layers and giving some weight based on their significant or groundwater potential assessment based on their significant. And after giving the weight, assessment to each thematic layer. Then the next step was checking the consistency ratio using the consistency ratio formula. And then after preparing the thematic layer, after giving the weight and the ranking of each thematic layer, the third step was weighting overlay analysis, or the aggregate of all the 9 thematic layers. And finally, I have prepared the final groundwater potential zone maps. And also I have applied sensitivity analysis methods. This sensitivity analysis method is very important to know the influence of each thematic layers on the final groundwater potential map using this formula, or by eliminating one thematic layer at a time and see or observe the final map of using the remaining thematic layers. And when it comes to the result and the discussion part of this work, the first thematic layer was the topographic elevation method, which is prepared from the digital elevation model. And as you see here, the red color is extremely highland areas, and the blue color, relatively the deep blue colors, is considered as the lowest elevation areas. And as a general, as a surface phenomena, the highest elevation are characterized as the high runoff, less infiltration, less recharge area, and they have deep static water levels. Therefore, I have given the weight or the low weight for the highest elevation areas. And when you see the lowest elevation areas, they have relatively high groundwater potential zones because of the there is low runoff, there is high infiltration, and also there is a shallow static water levels. And these lowest elevation areas are considered as a good groundwater potential zones. The second thematic layer was the slope, and from the slope map, I have classified the study area into 6 slope areas, from 0 up to 5, from 5 to 10, 10 to 15, and 50 to 25, and greater than 35. Therefore, the area which is characterized greater than 35 degree of slope, they are considered as a very, very low groundwater potential zones because of they are characterized as a rapid runoff and increased erosion due to their steep slopes. And
Ababa, you have about 2 minutes more, so please let's go to your results and then your discussion. Thank you.
Okay, and when you see the drainage density as well as the low drainage density areas, they are characterized as a good groundwater occurrences. They have high infiltration, low surface runoff, and they have a better groundwater potential zones. And these low drainage density areas have high amount of weights based on the Sati principle. And the other is the NDVI, the normalized different vegetation index maps, which is prepared from the near infrared minus red, or from the 2 band widths from the Landsat 8 imaginaries, and the negative NDVI considered as the waters, and they are clearly shown here. And low or approach to positive NDVIs are considered as sharplands and grasslands, and the weight is given based on their significance on the final maps. And it is the geological maps. From the geological maps, mainly the alluvial soils and the alluvial soils have relatively much higher groundwater potential zones, and they have high weights. And also land is land cover maps, also one has factors or parameters that affect this potential maps, and the highest rank was given to the forests and water bodies. And soils have also its own significant on water potential sites, and relatively the electric vertisoil and lithic liposoil have low permeability and they have low weights. And geomorphology, the valley floor has highest elevation, they have high value because of their excellent groundwater occurrences, and rainfall, high rainfall has high potential zones. And finally, the combination of these 9 thematic layers gives this groundwater final maps, which have high potential map is located in the southern part of the study area, and in the northern part of the study area, they have low and very poor groundwater potential zones. This is verified using the well yield data. The well yield data shows that the high elevation, the high potential zones have high yield data, and this confirms the field verification. And also from the sensitivity analysis map, the slope has the higher sensitivity analysis method. And when it comes to the conclusion from the spatial distribution of groundwater, highly related to slopes from the sensitivity analysis, and the majority of the study area fails good groundwater potential zones, and this cannot meet our demands. And when you see the verification of the final map with the well-yield data, 82% of the data are agreed with the final potential maps, and sensitivity from the sensitivity analysis map, slope is the most sensitive parameter. And the very good and good groundwater potential zones are located in the gentle slope and just like that. And finally, I want to recommend that groundwater flow modeling and petrographic study are very important to further now the subsurface flow and further to now the rock water interaction and the mineral characteristics. And this is how the water scarcity challenges our the world, or it is the most challenging area. And this is all about my presentation. Thank you very much.
Thank you so much. Thank you so much, Ababel, for keeping to the time, and then also for speedy presentation. Couple of questions, I guess. Panelists are here. Tesfa, please go ahead. Unmute yourself and go ahead.
Okay, thank you. Thank you very much. Thank you also, Nargacho. It's a very nice presentation. I have one or two questions, very short. One is you have used the elevation as one of the parameters for the groundwater potential evaluation in your study area.
Yes.
In your statement, you said that high elevation correlates with low runoff. I think high runoff. So,
yes.
Is that always true? I mean, doesn't it depend on the morphology of your catchment? Is it always necessary that high elevation areas have low potential groundwater? I mean, in your study area, with reference to your study, how do you explain it? The second one is groundwater potential, it says groundwater potential assessment, and based on the themes or the thematic layers you have used, what I would assume was that you have used all the superficial parameters that will tell you how much groundwater recharge can be there in a certain area.
Yes.
If I have not mistaken, I have not seen any characterization of the subsurface conditions of your study area. So wouldn't it be better to call it groundwater prospect zonation instead of groundwater potential zonation? Because I would say groundwater potential zonation would attach the potential, the quantity aspect of the groundwater in the study area. What do you think about this aspect of your case?
Okay. Thank you, Tesfamichael, for your nice question. As you know, the surface morphologies, many of the surface waters are the direct replicants of the groundwaters. And I have used the 9 thematic layers. Most of these 9 thematic layers are superficial, and they are the direct indicator of the presence of groundwater zone areas. And I have validated this superficial, whether these superficial phenomena have the direct relation with the groundwater. I have used some validations from the well-yield data. And I have taken the 33 well-yield data from the borehole data, based on their yields. And among the 33 well-yield data, 82 data have completely agreed with the final potential maps. This indicates that most of the vegetation area, the land use land covers, the normalized differential vegetation index, the slope, the elevation, all these 9 thematic layers have the direct replicant or the direct indicator for the presence of the subsurface waters. If you see, for example, if there's an anomalous vegetation in a certain area, it is also the direct indicator for the presence of subsurface waters. When it comes to the, when you said the elevation, I have used elevation is one of the parameters for affecting the groundwater potential zones. And if there is no any surfacial structures as well as subsurface structures, therefore, the highest elevation areas, if you see the Guna Mountains, the Gugufto Mountains, the Choke Mountains, especially more the highland areas, which are known as the high elevation areas, they are considered as a recharge zones, but there is a high run of areas, especially due to the drought condition, due to the non-vegetated areas there is a high runoff and also there's a low infiltration rate, as well as the static water level. When you measure the static water layer from the top layer to the water table, there is a very large amount, or there is a large depth. But when you go down to the downstream or from the discharge areas, relatively in the low elevation areas, you can find that there is at a very low distance, you can find, or you can get the static water levels or the water tables easily. So if there is no surfacial or subsurfacial structural or any lineament that affect as a barrier, therefore elevation can be used as a parameter for identifying the groundwater potential zone areas.
Okay.
Have you got me?
Yeah, thank you. Thank you very much. Ababe, I think we will make progress. Ahmed, are you here?
Hello, Edward.
Hi.
Hello,
Good.
everyone.
Perfect. So
Yeah, I'm
please
here.
share your screen and then your presentation. So Ahmed will give us a talk on estimating groundwater levels and analysis of trends in data scarce region using machine learning. Thank you, Ahmed. The floor is yours.
Do you see my screen?
Yes.
Okay. Hello, everyone. So my name is Ahmed Al-Azari. I'm a PhD student in a joint PhD between UM6P and UQAM at Canada. And today I will be presenting estimating groundwater levels and analyzing trends in data scarce regions based on machine learning. So I will be presenting at the beginning the research context, research question and objectives, the study area, and after that the materials, the results, and the conclusions. Of course, I will not present all of the results, but like some of the results. So I will start by setting the broader context of this research. Groundwater is the main source of fresh water in arid and semi-arid regions, providing over 70,000 of total water use. But this groundwater is often stored in shallow and vulnerable aquifers. It is slowly recharged or even non-renewable, and it's overexploited, which threaten its sustainability. A major challenge we face is also the data scarcity. So monitoring wells are sparse, irregular, and sometimes full of gaps. This makes it very difficult to evaluate groundwater dynamics properly. And this is important because many recent studies rely on hydrological and groundwater models to understand processes and predict future scenarios. But to run these models, we need two essential inputs: reliable climate data, especially precipitation, and consistent groundwater level records. Unfortunately, we don't have that much data sometimes. So one possible pathway is to use precipitation data sets as indirect indicators. Reanalysis precipitation products, which first developed in the late 70s, combine observation with models. They give us long-term climate records and global coverage, but at lower resolution. While satellite-based precipitation products, they provide high resolution, near real-time data, though with shorter records and some challenges in complex terrains. And the other possible pathway is to reconstruct missing groundwater data with different machine learning methods and AI methods. And one of the most used is the random forest imputation, which is a machine learning approach that learns from observed patterns in order to estimate values. So our guiding research question is to answer like how reliable are remote sensing precipitation products across different spatial and temporal scales, and to what extent can they support the imputation of groundwater level data, particularly in high altitude and complex terrain regions. So to answer this, we had four objectives: evaluate these products at different scale, daily, monthly, and compare strength and limitation in capturing variability, analyze the role of altitude in seasonality, and assess their potential for imputing missing groundwater levels. So the study area is in the center part of Morocco, and it's called the Tessouth Basin, covering about 9,000 square kilometers. It includes flat plains and high Atlas mountains that can reach 4,000 meters of altitude. And the precipitation here is between 200 and 500 millimeters annually. This is the average. While the temperature can vary a lot, like between 0 at the minimum and sometimes above 40 degrees Celsius. So we tested widely used data sets. So based on the most used data sets in regions like semi-arid regions and previous studies, we chose 10 products, 6 RPPs products, which are reanalysis precipitation products, and 4 of SPPs. And their time coverage differs. It spans from 1979 to present, and sometimes the coverage was less. And so what we did is that we did a comparison from daily, monthly, and seasonally. We made an evaluation by comparing the data sets with 16 weather station, observed station, and also 20 piezometers. And so these were used to evaluate these products at different time scales. To import missing groundwater data, we compared two methods. So the MICE method, which is multiple imputation by chained equations, a robust statistical approach, and random forest, which is a machine learning approach, particularly in nonlinear and complex data sets. And also we conducted a non-stationarity test before using all of this in order to see if, because as many models assume stationarity, so we needed to use the augmented Darcy-Fuller test in order to test the null hypothesis. So regarding the results, so the results show that most of the RPPs consistently outperform the SPPs. Again, this is like the analysis, and this is the satellite-based products, especially at monthly time scale. So we noticed that at daily scale, we had some good correlation, but it wasn't enough. But at monthly, we can see that the correlation has improved. And especially with ERA5. If ERA5 outperformed all of the other products and shown some really good results and some really promising good results that in future probably people can use them, of course, with attention, but yeah, we can use them. While the SPP's product have struggled a lot, especially in the daily, and in the monthly, they kind of improved, but it wasn't that improvement that we wanted in order to like compare them with groundwater. So as I mentioned, ERA5 based dataset gave the most accurate result. They tended a little bit to overestimate precipitation. So if anyone wants to use them, he will just need to correct a little bit this overestimation. And also we noticed that the altitude played an important role. Datasets were more accurate in plains, but less reliable in high altitude regions like the Atlas Mountains. And this highlights the need to adapt dataset selection to local topography. The imputation was repeated 20 times We did 20 iteration for 20 data sets and with different data sets for robustness. We used 80% of data for training and 20% for validation. And also we used the distribution plots in order to see how relevant this imputation is. And the distribution plot showed that imputed value matched the observed groundwater levels quite well. This confirmed that even with no direct correlation to precipitation on short scales, machine learning could still capture reliable long-term patterns. For groundwater, because we did the imputation for both precipitation in groundwater, but we wanted really to test the limits for the groundwater, because in the precipitation it's kind of less easier. For groundwater imputation, the combination of mice and random forest produced excellent results within the square R of 0.98. And so really some good promising results. And on the right, you can see that imputed value followed the observed groundwater trends over 40 years, significantly improving the quality of records for long-term analysis. So in the blue was the observed. You can see that we had a lot of gaps. And of course, we can see that sometimes we have like some outliers, but this is also one of the limitation of the techniques. If we don't have enough data, we can't extrapolate that much because otherwise we can have some outliers. But what we can do is that we can use them in order to fill the gaps within like a time series. The extrapolation is still, we still need to do a lot of things in order to improve that. So when we compare the precipitation product directly with groundwater levels, correlation were at the beginning weak, very weak. So we introduced a lag of 2 months. And then we noticed that an improvement of the correlation in some of the piezometers, especially this one and this one. And so we wanted to understand why exactly these 2 points. And what we noticed is that these 2 points were exactly shallow and close to the recharge area, which means that this is due to probably 3 factors. The presence of low renewable groundwater, like not connected to recent climate here, and this piezometer are measuring this. So it means that these ones are deep and probably not renewable or low renewable. The delayed recharge processes, especially that since we made a lag and we started to see some improvement in the correlation, this means that there is a delayed recharge, which is normal in like hydrogeology. And also intensive pumping, which masks the natural rainfall groundwater relationship. And this contrasts with studies in less exploited aquifers, which show stronger correlation between the recharge, precipitation, and also the groundwater. Okay, to conclude, reanalysis precipitation products performed better than satellite only datasets, especially at the monthly scale. Altitude and seasonality strongly influence datasets reliability. Direct rainfall groundwater correlation remain weak due to delayed recharge and overpumping, and probably heterogeneous piezometers, some deep and shallow ones. But importantly, machine learning imputation combining mice and random forests provided highly accurate reconstructions of groundwater levels with long-term consistency. So this study shows that even in data-scarce environments, remote sensing combined with AI can improve groundwater datasets, strengthen modeling, and ultimately support more sustainable water management in arid and semi-arid regions. Here are the references, and thank you for your listening. And this work has been published recently on groundwater for sustainable development. Thank you for your listening.
Thank you so much, Ahmed, for giving the time and for the clear and insightful presentation. I think we have room for questions, 3 minutes for questions, to take some questions. I think I will ask you one. The computed groundwater levels that you have there, that's the ensemble, right? Those are the ensemble averages or median
Yeah,
or okay.
yeah, exactly.
Okay.
Yeah, exactly. The data sets, because we downloaded the daily data sets and we needed to aggregate them. Like for instance, when we were using like precipitation for the monthly, we made the aggregation, so we made the sum. But when we wanted to do like the seasonality, we did also the same thing. And what with the annually, sometimes we did like the median in order to compare them with the groundwater level. But most of the time we use the sum of the precipitation from daily to monthly to seasonally.
Okay. Prof. Seifu.
Yeah, excellent job. I really enjoyed listening to your presentation and very promising. And then I was wondering on the choice of the scale of your study area. Given that most of this data could be available at a larger spatial extent, what is the prospect of applying this at, let's say, regional scale? And then would that scale determine the outcome? Or as a reasoning behind just choosing that small area, did you want to test a particular situation like role of mountains or recharge zones? So what was the purpose of choosing? Yeah. So
yeah.
This is very promising and can be scaled at once
I get your thank you for your question. Actually, my PhD is focusing on this study area because it's one of the most groundwater stressed regions in Morocco, and also the strong data scarcity makes it like a relevant case to test methods for filling data gaps, because this study area, it's nothing has been done before, and we wanted to try a lot of things and we don't have data, and we want to do a groundwater model and a integrated hydrological model, and we don't have enough data. So what we wanted to do is that to test if these products and these methods can help overcome this data scarcity in such type of regions. And unfortunately, we didn't have like more data for like more like for bigger scale. What we had is that the data of this watershed. So that's why we wanted to test all of data that we have in this watershed. And it's kind of, yeah, it's at least it's 9,000 square kilometer. So it's bigger enough to test, and also it has like multiple topography distribution. It has like the plains, so we can go from 400 meter of altitude to 4,000, which is kind of it gives us like a large scale to test everything. And also we had enough piezometers in order to test it in this aquifer. And also the important thing in this study area is that this we know exactly like the limits of the watershed and also the limit of the aquifer. So we have kind of some knowledge in order to test this. While in other regions, probably we can lack some data and some understanding. And so, yeah, that's why we exactly choose this study area. And also because it's my main study area for my PhD.
Excellent, Ahmed. Just to call your attention to the ongoing data collection activities as highlighted yesterday by the regional representatives from the regional economic commissions in Southern Africa, in Eastern Africa, and in ECOWAS. Data is being put into database systems, information systems, and then there is a scope for you to scale this. Okay.
Okay, yeah, we can probably continue the discussion after, or that would be interesting. Thank you for the information.
Is there any other question? Otherwise, we make progress. Thank you so much, Ahmed. We will have other discussions.
Okay, yeah, thank you. Thank you, everyone.
Yeah. So we have Abdallah. Abdallah, please.
Edward, would you please get closer to the mic?
Can you hear me?
Good afternoon.
Yeah, good. Please, share your screen and then let's make progress.
Absolutely. Yes, sir.
So Abdallah will be presenting on harnessing groundwater opportunities in the Kagera Aquifer through innovative MAR solutions. Please put it in a presentation mode and then we'll be good to go.
Good afternoon, everyone.
Good afternoon. Thank you.
I would like to thank the committee for organizing this event. The work I will be presenting today is the result of an MBI Nile Basin Initiative study that was funded by the GEF and the UNDP. So I'd like to recognize their contributions. My name is Abdullah Shigidi. Dr. Maha Ismail is the lead of the MBI program, Groundwater program. A number of experts actually contributed to this study. And the MBI project is basically was one of trying to enhance the knowledge about 3 transboundary aquifers in the Nile Basin, of which Kagera is only one of them. And basically to try to improve knowledge about these systems and enhance their the ability to develop them and develop sustainably many of them. This is the Kagera Basin. It's at the headwater of the Nile Basin. And the name gets the Kagera River is a dominant hydrological factor or hydrological is the dominant hydrological attribute of this basin. The basin has an area of about 60,000 square kilometers. It's shared by 4 countries, Tanzania, Rwanda, Burundi, and Uganda. And it has its altitude goes from about 4,500 meters to up to Lake Victoria at the levels of about 1,200 meters above sea level. The Kagera Aquifer is an integral part of this basin. It only resides in about 10% of the 60,000 kilometer basin, Kagera Basin. The aquifer is basically formed from the alluvium deposits close to and around the Kagera River. The Kagera River, you can see, you might not be able to see it clearly. It goes with the boundary. I'm trying to go follow it. It grows with the boundary of the 4 countries. It's forming the boundary for the most part between the countries. And you can see the green, it's represented in green color, the alluvium deposits that forms the Kagera Aquifer. It is surrounded for the most part by basement complex and underlain by basement complex for the most part. Aquifer thickness varies from few meters at the upstream end in the Burundi and up to about more than 80 meters close to Lake Victoria. The study included an assessment of the potential of the aquifer, including determining storage the capacity and safe yield. Storage of the aquifer was estimated to be about 50 billion cubic meter. Groundwater modeling was conducted for that. Safe yield of 20 million cubic meter per year was estimated to be possible. Annual recharges 40 to 50 million, about 40 million cubic meter per year, emanating mainly from the Kagera River itself, which is seen here in dark blue, as well as surface runoff and fracture flow from the surrounding basement formations. This figure shows the Kagera Aquifer, and about 1 million persons lives within the Kagera Aquifer boundary, this area. So it's actually considered a little bit highly densely populated. And let's divide it into 3 segments. All of them are connected, hydrological connected. The first segment is the upstream segment. It's very narrow, 1 kilometer, and it's very shallow, less than 10 meters. The second segment is the middle segment, 5 to 8 kilometers wide. And the third segment is a delta segment. which constitutes about 70% of the aquifer area shared between Uganda and Tanzania. There is actually significant groundwater resources in this aquifer, and it's underutilized. As I said, its estimated usage is about 5 million cubic meter per year at the most. And there are issues with groundwater, with water availability for the local communities in these areas. And development of groundwater resources in this aquifer are not simple. It's easier in the delta segment, which have significant depths. But in these shallow areas, in the middle segment and upstream segment, it's quite difficult. Conventional boreholes, they do not actually function well. And I have to add that these are alluvial deposits that are very low permeability. In some places, actually, it's underlain by fractured basement, particularly in the in the upstream and in the delta segments. This figure here shows what the points we have here are basically the houses or the settlements, or trying to identify the areas where the population would be in need of drinking water. And there is a significant drinking water problem in the area, particularly in the middle segment and the upstream segments. The people, for the most part, this is basically shows the prevalent landscape in the study region. And it's basically a rolling hill area whereby the people live in the high areas. You can see some houses in here. And the water resources, and these are basically basement complexes with most of the time no groundwater. And the people rely on rain for precipitation, which is a significant amount of precipitation. But for perennial water, they do have to travel to the river or to the streams at the low areas. And there is also the groundwater, of course, is surrounding these areas, the alluvial deposits at these particular low areas, and it's an abundance, actually. So the challenge is to try to meet the demands, the water demands, particularly for domestic water supply for these communities. And this shows some of the activities, some of the domestic water supply situation in the area. This is a hand pump, an unoperational hand pump. This pump was established in 2021. By 2023, it was non-operational. There were about 10 of them in one area. They were basically constructed in the basement area, trying to abstract water from the fractured zones, but they went dry quickly. They became non-operational. And here you can see some of the local community children who are walking up after collecting water from the river or from a well, a pumping well that is away from their communities. Here is a depression that people are just getting water from. Here we have an operational hand pump, and these are basically found mainly in the Delta region, in Tanzania and Uganda, as you said, where, but there is a problem with extensive use of these types of wells, is that in some areas they are causing significant drawdowns, and it's taking longer to recharge. These are ephemeral means. These are also some of the water supply options. This is a spring at the foothill, and you can see this is the distance. The people live uphill. There's quite a significant distance still to the river, but they have an ephemeral spring here. And again, water supply from that. And this is basically a pit. This is a groundwater, groundwater in a low area. People dug this pit and they started taking water just for their use. So the situation needs improvement. And the idea is to try to use groundwater to provide safe drinking water supply. We identified potential, so there is a groundwater is available. We identified a number of interventions that we thought would basically assist in elevating the situation. Is through the use of a number of MAR techniques, bank filtration in the low areas, and water. The proposed techniques were as follows. These were generally the idea. First of all, water spreading in the delta area to try to raise the depleted groundwater in the areas in which there is heavy pumping. The green areas, which we can see in here, these...
Prof, please, you have 1 more minute to conclude. Thank you.
Okay, I'll go quickly. This can use channel modification. Bank filtration is proposed for the low areas. The idea is to have a water source, a trench in the low area, connected. This will abstract water, put it to a tank, then to a water distribution system to the community. It's basically the removal of the alluvial deposits, the low permeability soil, replacing it by gravel and sand of high permeability. This can be increased, basically aligned so that it intercepts the natural groundwater flow, and it acts as a storage. Horizontal screens are proposed to drill, to pump the water up to the tank, and basically an electric pump, photovoltaic cell or solar panel could be conducted. This could easily be dug as needed to try to provide abstract water from the groundwater. Then the river would basically supply the abstracted water by, as a low point would be induced to induce flow from the river to recharge the pit and the aquifer. The solution can be implemented throughout the rural areas. It's scalable, can be to different communities according to size. It's can be repeated, and it's relatively easy to construct and maintain. It's centralized, scalable, centralized solution. There are problems that is susceptible to anthropogenic activities and prone to flooding. We recommended that after geotech tile be used to cover the material, and so as to prevent any contamination to the water. The project, the design had been adopted by the community, by the officials in 3 countries, or in the riparian countries. 3 pilot projects have been selected, located. Construction for this pilot project is supposed to start this month, coming September 2025, in Rwanda, Burundi, and Uganda. Thank you very much.
Thank you very, very much, Prof. I think we have 2 minutes for questions, and then we move to the next presentation. Is there any question? I can't see any question. Okay, we move to the next presentation. We have Keshao.
Yes, I'm here.
Yeah, please share your screen and let's make progress.
Okay.
Thank you.
It's okay?
Yes, please. Let's make progress. So, Paul. Oh, sorry. Yeah. Go ahead.
First of all, I would like to thank the organizing committee that created this opportunity. My name is Gashaw Tesfamichael from University of Gondar, Ethiopia. Here are the lists of the co-authors. The title that I will present is Groundwater Exploration and Potential Water Well Site Selection in Underground University of Gondar. So these are the outlines that I will present. Introduction, objective, methodology, approach, and the procedures, as well as results. So as introduction, University of Gondar is currently facing with a significant water scarcity issue that affects the teaching, learning processes, and research activities. This persistent lack of adequate water supply has hindered daily activities, disrupts academic schedules, and impacted the overall quality of life on campus. The implications of water scarcity extends beyond mere inconvenience. They threaten the health and well-being of students and staff, as well as disrupt educational process, as I told you before. and potentially deter prospective students from enrollment. Insufficient water supply can lead to unsanitary conditions, which may exacerbate or aggravate health problems and negatively impact academic performance. Therefore, addressing this critical issue is paramount to ensuring that Gondar University remains vibrant and healthy place for education and community engagement. As you can see, the laboratory are stopped working because of water, because of the shortage of water. Students, as you can observe here, are suffering by shortage of water. So our objective was to select potential water well sites and determine provisional drilling depths, diameter, and methods of drilling, and also casings to be installed. Specifically, geological and hydrogeological, geological and structural identification, conducting geophysical investigation, aquifer characterization, groundwater potential site selection, and determining the well depths and diameters was performed in this study. The location of the catchment is this. This is nearby University of Gondar. When it comes to approach and procedures, exploration has been carried out in 3 stages, like desk study, field survey, and analysis and interpretation. In desk study, we have observed, collect geological and hydrogeological maps and reports, and topographical maps, borehole data, meteorological data like rainfall, temperature, and wind speed and sunshine duration, as well as digital elevation model have been used in this study. Satellite image is also used to extract geological structures like this, and we develop this or delineate these geological structures or lineaments from satellite image. So borehole camera observation also have taken, and pumping test review also conducted. In the field survey, project members accomplish a variety of critical tasks during the field work, like soil type observation and its textures and thickness of soil type, as well as ecological unit identification, geological structural measurement, analysis, and interpretation, geomorphological observation, hydrogeological evaluation, as well as recharge and discharge zones identification, and finally potential well site selection was performed. In addition to that, inventory of existing water points that are existed in the catchment and geophysical surveys, basically magnetic and electrical resistivity method, have been conducted in this study. The post-field work, basically analysis and interpretation, have been conducted after finishing the field work and after collecting the disk data. We have collaborated this data to analysis this study. So in the recharge estimation, we have used a wet space model to estimate the recharge of this catchment. This weights plus model can use this elevation, land use, soil type, slope, rainfall, potential evapotranspiration, temperature, wind speed, and groundwater depth data as an input in the form of map, ASCII form, and it can give results in the form of map. In its results, it can give 3 results that is called runoff, potential, actually evapotranspiration, as well as recharge. So we have used this model. These are the inputs of the model. So when it comes to the outputs, geology and hydrogeology of the catchment is observed. There are 5 lithological units that have been identified during the field, like unconsolidated sediments, slightly weathered aphanitic basalt, moderately weathered aphanitic basalt, and vesicular basalt. Actually, vesicular basalt is not mappable in our map scale. So our geological map looks like this. So as you
have 3 minutes. Do you want to go to your final results and then your conclusion?
Okay, I'll go fast. So the unconsolidated sediment looks like this. It is very thin that cannot store water because it's very thin. So the slightly weathered basalt is also not good for an aquifer. We chose the moderately to highly weathered and fractured aphanitic basalt for the promising aquifer in this catchment because of their criteria when we characterize the aquifer. The groundwater recharge estimation and the total storage. As I told you before, the recharge, surface runoff, evapotranspiration are produced in this model. As you can observe here, this is the result of the model in the form of map, and the recharge that has been estimated is 83.1 millimeter, which is 6.76% of rainfall that are infiltrated to the ground. The geophysical method, basically we have used electrical resistivity method and magnetic method for this study. So in the electrical resistivity method, a base method is selected here, and the result is in such like. So layer in the first base point, the layer 5 is selected, as well as in the second layer, second base point, the last layer and layer 5 and last layer called layer 7 is good for groundwater site. And also in the base 3, this layer is very good, layer 6, as well as in base 4. As you can observe, layer 4 is important for groundwater site. And magnetic method is also accomplished here. So as you can observe, the blue part is very promising for groundwater well site selection. Unfortunately, we have conducted 2 sites for magnetic method because of noising. So the result of just 2 sites are in such like. Finally, the sites were selected based on various criteria, including proximity to existing infrastructure, accessibility, and potential yield of groundwater. So we have selected 3 well sites like this, as you can observe in the map. Community school, nearby community school is very potential, and the bridge site as well as near Fasil campus is also selected. When it comes to well depth and the diameter, we have designed the well depths, like the first community school site should be 150 meter depth, and the drilling type should be DTH, as well as casing type will be PVC with an 8 diameter, internal casing diameter. So the location is like this. And the bridge also 150 meter DTH and PVC with 8 as such like community school. And the Fasil campus 250 meter DTH steel casing. We use steel casing and yes, please. Okay. Thank you.
Okay. Thank you very, very much.
Thank you.
Yeah, so I was talking about the amount of work they've done and also some of the features that they selected in terms of taking into account evapotranspiration when they were looking for potential recharge areas, which is very important. I wasn't seeing that in the earlier analysis that were being presented. And so I think I like this. Thank you. I leave it to you, Prof, and then the rest of the team. I think we've come to the end of the presentation. Thank you.
Thank you.
Yeah. Okay. Thank you so much, Edward, for chairing, and Bahaidu and Lydia and Olivia for chairing the sessions today. And then it was such another excellent day, I may say. And then tomorrow, dear colleagues, tomorrow we'll have our final day whereby we have one keynote address by Professor Sheikh Guy, a seasoned hydrogeologist from Senegal with so many international experience, and we'll hear from him tomorrow. And then I will have survey results that will show us where we are with respect to research and education in Africa based on the survey results and what has been captured during the submission of your abstracts. And we'll also have a short draft resolution on, as a first gathering, what our visions and aspirations are. And the draft will be circulated tomorrow morning, and then in the afternoon we'll read that out. If you have comments, you'll provide comments, and that is what I can say. And then generally, the content and the quality of the presentations are, very good, excellent. Some amazing works. And so this also shows the spread of the research activities, the type of work, different type of sample works happening currently. And then there is some pattern that we'll have to keep and move forward with it and grasp. There are other aspects of, activities, research activities, we'll need to update and leave it behind in the future, considering the various comments that has been provided by seasoned experts like Alan Macdonald, Dan Olago, and even the video by Grant Ferguson highlighting the need for data and field work and field evidence, and then put the human mind into it, or nowadays machine learning into it, but the data, based on data, and making actionable, converting that into actionable knowledge. And so focus more on quantitative works, and then also the need to bridge this hydraulics and tracer-based approaches. And yeah, nothing will replace the field work and field-based, data-based decision-taking. The data may be processed in qualitative way, like overlay analysis that is proliferating in many places. But with the emergence of machine learning, I think data can be interpreted in much quantitative way. And then, yeah, so tomorrow let's assemble again, and then the focus is going to be on emerging challenges on water quality, and some excellent abstracts from Western Africa and Eastern Africa. So let's come tomorrow. Please tell your colleagues to join us tomorrow. It is a very important day as we are going to reflect our views to the world. Yeah, so well done, everybody. And yeah, I congratulate you all, the presenters and team members, organizing team members. So let's meet tomorrow. Thank you so much. So meeting adjourned today.
Thanks, everyone. See you tomorrow.
See you tomorrow.
See you. Thank you so much.
Thank you. Thank you tomorrow.